Good morning and welcome to this conference on environmental intelligence. Thank you to you all for being here. Thank you to our esteemed guest speakers. We'd like to thank as well the Alan Turing Institute for their support, and in particular Sir Adrian Smith, who will provide our opening presentation. And finally, I really must acknowledge the special efforts of the Exeter University and Met Office conference teams who've worked tirelessly to arrange this conference against a very challenging backdrop, as you can imagine. This Environmental Intelligence Conference is co-hosted by the Met Office and our partners in the Joint Centre for Excellence in Environmental Intelligence, the University of Exeter. And you'll be hearing more about the Joint Centre later on from our co-directors, Gavin Shaddick and Kirsten Dale. We bring together presentations from leaders in the field, as well as interactive sessions providing the opportunity to discuss priorities and challenges in this important area. Our changing environment presents a series of interrelated challenges that will affect everybody's future health, safety, and prosperity. And environmental intelligence integrates environmental and sustainability research with data science, artificial intelligence, and cutting-edge digital techniques so that we can address these challenges collectively. And together we can apply AI and machine learning techniques to our vast environmental data sets. And we want to do that to extract meaning from the interaction between both disciplines and data sets. And some of the best examples we've already seen are where, for example, we provide forecasts of energy supply and demand, or look at the combination of concerns over food and water security and air quality. Environmental intelligence will be crucial in ensuring that we have the information required to enhance our resilience to environmental change, which is only going to be increasing, and that our future interactions with the natural environment are sustainable. For us here at the Met Office, advances in the field of data sciences, such as machine learning and AI, have the potential to improve our performance and skill and reduce our compute times, so we can really push the limits of weather and climate science. And that helps us address our key purpose of helping people stay safe and thrive. And now's the right time to be making progress in this area. We know that we're approaching the 26th Conference of the Parties, COP26 in Glasgow. And as in previous years, the Met Office Hadley Centre has been contributing important research and data to that conference. And they are celebrating their 30th anniversary this year, which should have coincided with COP as it was originally planned. So I hope this Environmental Intelligence Conference is the first of many. It's an important early step in helping us get to know one another and to explore how we can work together to address important environmental challenges such as climate change. This is a public conversation and one that we should lead. It's now my pleasure to hand over to our co-hosts for this conference at the University of Exeter, and particularly to Professor Lisa Roberts, their Vice-Chancellor. I'm sorry we couldn't be together today, Lisa, but I can already say with truth it's been a great pleasure working with you. Thank you.
Good morning, everyone. I'm Professor Lisa Roberts, and I'm the Vice-Chancellor of the University of Exeter. And I'm absolutely delighted to welcome you this morning and to be jointly opening this conference today with Penny. I joined Exeter back in September, and one of the striking things about Exeter that I've quickly become very proud of is the truly stunning scale and quality of expertise in environmental and climate research in the city. Across the university, we have over 300 people working in environment and sustainability research, which together with our colleagues at the Met Office means that we're ideally placed to play a leading role in developing solutions to some of the most pressing societal challenges. And like all global challenges, addressing the impact of environmental and climate change requires not only an interdisciplinary approach, but a joined-up approach, not just across academia, but also with businesses, charities, policymakers, and wider society, in order that we can find solutions that result in tangible change and meaningful progress. And that is what we have in the city of Exeter, and I think it's truly impressive. Everyone at the university is very proud of our strategic partnership with the Met Office, and of our work with all of our partner institutions, especially the incredible contribution that we collectively make in influencing government strategy and international work in this arena, particularly the IPCC. With the Met Office specifically, we have many existing collaborations, including joint research projects and papers, a number of joint academic positions, for example, the 9 recent new appointments in our Global Systems Institute. And as we look forward, there are so many exciting opportunities for further collaboration working on our shared priorities. And as organisations, we can be at the forefront of the green recovery from the COVID-19 pandemic, locally, nationally, and globally. Last year, as the university, we took the step of making a public declaration of an environment and climate emergency. And we brought together some of our leading academics, staff, and students who developed a plan which focused on the actions required based on evidence and science. And this pivotal work has transformed the university's approach to sustainability, and for which we were really happy to have won the Guardian University Award for Sustainability last week. Our partnership with the Met Office has just entered an exciting new phase with the establishment of the Joint Centre for Excellence in Environmental Intelligence. Our interaction with the natural environment plays a crucial role in all aspects of society, and our ability to fully exploit the power of data will be crucial in addressing the challenges associated with environmental change. Aligning recent advances in data science and AI with an explosion in environmentally related data presents us with an exceptional opportunity to transform our understanding of the complex interactions between the environment, climate, natural ecosystems, human, social, and economic systems, and to develop tools that will enable informed decision-making. The Joint Centre will be an international thought leader in the field of environmental intelligence, and working with partners will position the UK as a global trailblazer in this rapidly evolving area of strategic global importance. By its very nature, this new field of environmental intelligence requires a truly trans and interdisciplinary approach, crossing disciplines and working with partners and stakeholders to ensure that our research has maximum real-world impact. Initial research themes will include climate change, clean air, COVID-19, and extreme weather events and natural disasters. In addition, the Joint Centre is hoping to deliver innovative interdisciplinary education and training for a new generation of leaders who are going to use AI to develop solutions to enhance the resilience of individuals, communities, businesses, and governments in the face of environmental and climatic change. Both partner organisations have made a long-term commitment to supporting and resourcing the Joint Centre, and we're also really excited about the collaboration opportunities with the wider environmental intelligence and data science community. I'm delighted that Sir Adrian Smith, Institute Director and Chief Executive of the Alan Turing Institute and President-elect of the Royal Society, has undertaken the role of Special Advisor to the Joint Centre, and we look forward to working closely with our partners at the Alan Turing Institute and many of you in the future to bring together the national data science, AI and environmental sciences communities to address these most important of global challenges. The University of Exeter is proud to be one of 13 partner universities with the Turing Institute. Within our Institute for Data Science and Artificial Intelligence at the university, we're really glad that we host 23 Turing Fellows and are part of a number of Turing-sponsored research projects. So pleased that Sir Adrian's been able to join us for this conference. Just remains for me to thank you all for attending, and I hope that you enjoy the day.
Well, can I add my welcome to everyone for this important conference, and thank you for having me, even at a distance, and happy Christmas to everyone. So I'm going to begin my talk with an introduction to the Alan Turing Institute, the UK's National Institute for Data Science and AI. Why Turing? Well, most of you will know Turing did incredibly pioneering work in mathematics, in engineering, computing, and if you look back, most of the key disciplines that now underpin data science and AI, a lot of the origins go back to Alan Turing. And what do we try to do in his name? Well, at heart, innovate and develop world-class research in data science and AI, but much of it motivated and aiming to solve real-world problems. And there's so much challenge out there that it's very important for us to train, encourage new generations to work in this area. And there are interfaces with policy and public concerns that we need to take account of. So one of our roles is to be the go-to place for advice in that general space. It's very hard on one side to say what Turing is and what it does. So here's an attempt. Around the outside, there's the real world that throws up challenges, economic challenges, health challenges, security challenges, and that feeds into theoretical work in the foundations of data science and AI, which in itself then leads to tools, practices, and systems that can be exported back into that real world to apply and solve problems. But we have to do that recognizing that there are potential dangers to this stuff in terms of privacy and biases and fairness and all sorts of concerns. And so at the heart of our work, we want to do all this, bearing in mind a safe and ethical perspective. And this leads us to be interested in policy. Do we need to regulate some of the things that come out of this? And how do we govern the use of data and algorithms? So who are we at Turing? Well, at heart, we're a wide-ranging university network, currently 13 university partners spread widely throughout the UK. But in addition, a number of partners and collaborators drawn from business, industry, government, charities, local government, global corporates. These are our partners who throw up, as it were, the challenges to which we respond with the basic research innovation and hopefully the tools, practices, and systems that can go back into these partners to help make the world a better place. But this isn't a uniquely UK activity, of course. And so one of the roles of Turing as a national institute is to make contacts, respond to overtures from anywhere around the world, to build an international community, both interested in research, but also, of course, in the kind of standards and the safe and ethical issues that I referred to earlier. We need that to happen at an international level. So making things a little more focused, we could summarize at the moment a lot of what we do in a sector-specific way. And there are 6 basic sectors. For example, defense and security, data science for the way that science itself is changing, health, finance, and data-centric engineering. The man-made world is increasingly, in terms of bridges and tankers and airplanes and everything, embedding sensors that give us fantastic data to be able to monitor performance, maintenance, and the rest. And of course, cities and, how do we live in the future? Smart cities, air quality, road traffic, all the things that relate to the way we do our daily life. So between those 6, we're really responding to most of the challenges that are out there in the real world. So those are sector specific, but cutting across everything, all the insights and the conclusions and the tools are relevant to public policy, development of policy and its implementation, the very foundations of what artificial intelligence means and where it's going and what is the nature of the beast, and then concrete tools to help the outside world. But also, we're faced with major challenges in terms of sheer scale of data and the development of sheer scale of computing power that goes with it. And so when we're looking at algorithms and the challenges in problems, we're against an evolving background of just the sheer immensity, the scale at which all this happens. And can we adapt, and can we find tools, practices, and systems that will apply at that level? Who are we? So we have a process whereby our academic partners nominate and second Turing Fellows, and we currently have over 350 of those. We've been funding some Turing Research Fellows ourselves. These are some of the brightest and the best young folk. Encouragement and funding of PhD students, internships, and something very important and not entirely unique, but rather special for Turing, is our research engineering group, software engineering data scientists who have the ability to take abstraction and mathematical algorithms right the way through to open source code and programs that can actually be employed by those who don't necessarily know what's going on under the bonnet. And recently we have the new schemes of Turing Fellows and EPSRC Fellows. So this is very people-dependent enterprise, and that's a summary of who we are at the moment. Now, turning to the main themes of today's conference, environment, sustainability, let me just summarize some of the things we're up to, but give you a health warning that much of this is in a state of development, and we hope rapid development going forward. So we're evolving the Turing presence and activity in this area, but I'll summarize what we are doing in terms of programs and partners, who's involved, and perhaps interestingly, interest groups that have grown up among fellows who share particular kind of obsessions and interests, and out of that, of course, grows the research bids and proposals of the future and the research work. So our partners far and wide in this particular arena, I won't go through reading them all out, but we have global foundations who are funding for the general public good. Then we have those who are more focused, like, for example, National Grid. But just to say, we do span everything from the roads of London right through to the Antarctic in the activity that we've got at the moment, with agriculture tucked in somewhere along the way. So this is a very wide-ranging set of partners that we will build on going forward into the future. So the interest groups, we have Gavin and David who are leading this, but we have over 180 people who are really interested in getting deeply involved in this group activity. And there are some of the headings of what we are going to be looking at as we go forward. But I think perhaps that's the last one. There is a growing kind of sense that there are almost new careers and new kind of people we need to develop going forward. So the challenges that are out there, environmental data science as a career path really becomes something we need to think about. How to train the next generation, how to build a community around these challenges. So just some specifics. Here are three pretty pictures. Clouds. Most of this is machine learning to unravel complexity from various complex data sources. So machine learning classifying clouds, machine learning looking at climate and sea ice loss, machine learning looking at the rather new phenomenon of dangerous icebergs moving around using radar, satellite imagery. So these are kind of cutting edge, exciting examples where bringing machine learning to bear on masses of data is going to transform our understanding. Coming back from the Antarctic into peatlands and fields in general, lots of problems in terms of emissions from peatland. Agriculture. The climate change and agriculture, I think, is something we're all aware of, but we really need now to start drilling in on a much more concentrated basis. So wonderful challenges in agriculture. And coming back from the fields to the city, real-time sustainability of infrastructures, understanding air quality. We have a lot of work going on traffic flows. And a lot of this, of course, will be highly relevant to the really headline challenge of net zero, contributions to emissions from transport, from homes. We need to understand that in some depth. And so urban environments are a very serious kind of component of the net zero understanding going forward. And looking now a bit more globally, adaptation, resilience to climate change, ranging from everything from extreme weather to the effects on society itself in terms of migration and habitability, enormous kind of challenges and very exciting ones, but they're challenges at scale. So going back to some of the stuff I said earlier, getting people together now in groups and networks is going to be fundamental. These are beyond the work of individual scientists or individual university departments, which is why the kind of thing we're trying to drive forward today is so fundamentally important. And of course, at the heart of net zero, energy considerations, the greening of energy, the use of data science and AI to do, well, I was going to say forecasting, but we now have to try and do that as nowcasting, understanding things at a much faster level and deeper level. So there are long-term issues here in terms of energy, whether it's to do with homes, transport, whatever. Again, whole series of challenges that we haven't begun to scratch the surface of. And the whole kind of infrastructure and data and combining data fusion from many different sources, data that's on the surface, satellite data, and brought together with data-centric techniques in modeling and simulation. So in addition to the specific challenges, there are these kind of infrastructure and methodology challenges that we have to get to grips with, data fusion being a particular one. So what are we aspiring to do? Well, Turing is absolutely delighted to be in on the act here. As we go forward with new models and funding, hopefully post-spending reviews for the Turing itself, we will build and expand on our current collaboration with Met Office and Exeter, but also draw expertise from the wider university network, but also give greater priority to the issues and concerns in environment and sustainability. So looking more broadly, beyond Turing and beyond individual enterprises, where are we at in the UK in terms of understanding and perception of these challenges and what we need to do about them? The AI, as I speak, the AI Council is within days of issuing its UK AI roadmap, which in a sense sets out an overall strategy for what we need to do in the UK to fully exploit both the potential and the resources and the assets that we have in order to maximize use of data science and AI. Part of that, consultations have been going on national data strategy. It may be the unglamorous part compared with wonderful mathematical theorems and algorithms, but without data, the ability to access the data, to link the data, to have the data on a platform we can use whilst preserving privacy and other issues, we do need absolutely to get a clearer national data strategy. And all this is creating challenges. We need people to solve the problems, and we have a huge skills deficit in the arena of data science and AI in the UK. So I do think we need a data skills strategy, and I and others are trying to push to get a much more joined up debate on that. And as we begin to evolve algorithms that get out there and are affecting our daily lives, there will, of course, be a lot of debate on regulation and standards and Are these things safe or biased or whatever? And so we will continue to need to lead on a national debate in and around these rather sort of ethical and regulatory issues. So coming up in this year, there are very specific opportunities for the UK. Issues around the environment, climate are very central to countries in the G7, and the UK has the G7 presidency in this coming year, and there's a science stream which we will be getting together on. So that gives us, I think, opportunities. And of course, the big COP26 coming up around about November in next year. So environment, sustainability, all the issues with which this conference and these groups and networks we have today are concerned with, next year is a really big year. So thank you for listening to me. We're embarking in many ways on a journey into somewhat the unknown, but the challenges that confront us are exciting, but absolutely fundamental to all our futures. So thank you for listening to me, and good luck with all our work at the conference.
Hello, I'm Kirstine Dell from the Met Office, and I'm here with my colleague, Professor Gavin Shaddock from the University of Exeter. Together, we are the co-directors for the Joint Centre for Excellence in Environmental Intelligence and will be your guides through the conference. In this first section, Gavin and I have three very important jobs. First, to thank Sir Adrian Smith, Professor Penny Endersby, and Professor Lisa Roberts for officially opening the conference. Second, to welcome you all to the conference. Welcome. And third, to keep you here. Now, clearly, I can't lock the doors. So Gavin and I are going to do that by explaining to you why we think environmental intelligence is important, and then to entice you with a very exciting conference program. Next slide, please, Gavin. So there are periods in time when the pace of change, scientific development, and technological breakthrough accelerate. We're currently experiencing that in data sciences, where it's argued that we are in the midst of the fourth industrial revolution, bringing with it an unprecedented rate of change, disrupting almost every industry in every country. Three factors have combined to bring us to this point. First, we have access to volumes of data an order of magnitude greater than anything we have previously experienced. For example, the Met Office current operational and parallel suites produce a very healthy 18 terabytes of data every day. Second, there is much greater availability of high-performance computers. For example, at the Met Office, we are about to have a new high-performance computer that will bring with it a 6-fold increase in compute capacity and is expected to be the world's most advanced supercomputer dedicated to weather and climate. Third, we have the expertise, tools, and techniques to extract meaning and value from the data. For example, the Turing AI Fellowship Initiative attracts and trains the best research talent in AI. And earlier this year, UKRI announced a £100 million investment to create 1,000 new AI research and business leaders. As part of that funding, the University of Exeter launched a Centre for Doctoral Training in Environmental Intelligence, Data Science and AI for Sustainable Futures. This training is designed to equip the next generation of scientists with the tools and techniques that they need to extract the value from environmental data. Together, these three factors bring with them considerable opportunity, and this is acknowledged across a wide range of sectors. For example, this month, the Royal Society published its Digital Technology and the Planet, highlighting the enabling role of digital technology, including data, AI, and digital twins, in achieving the net zero emissions by 2050. An opportunity also echoed in the recently published National Data Strategy that in turn builds upon the Industrial Strategy, the AI Review, the AI Sector Deal, and the Research and Development Roadmap. So how is the UK responding to this opportunity? The UK government has stated that creating an economy that harnesses artificial intelligence and big data is one of the greatest opportunities of our age, and that we are at the cusp of one of the most exciting times in our lives. And if we get our strategy for AI right, we will be able to reap the rewards for our economy for decades to come. Critically, the UK is committed to seizing this opportunity, to putting the UK at the forefront of AI and the data revolution, acknowledging that we must act now if we are to be at the forefront of an industry that is going to shape the future and will have a transformative impact on society. The industrial strategy sets out 4 grand challenges that will put the UK at the forefront of the industries of the future. These are on the slide: aging society, artificial intelligence and data, clean growth, and future of mobility. This conference is going to consider 2 of these. So I've started quite broad. I'm now going to hand over to Gavin to bring this home and to outline how we, the Centre and this conference, fit into the story.
Welcome everyone, and I'd like to give my own thanks to all participants for joining us, and thanks again to Sir Adrian, Penny and Lisa for their opening remarks. And really I'm going to summarise what we're talking about, or what I think we're talking about today when we use the words environmental intelligence. And this is really drawing on those points made by our Sir Adrian, Lisa and Penny, and really reflecting on the fact that our interaction with the natural environment plays a crucial role in all aspects of our society: our health, wealth, safety and future development. And because of this explosion in the data that's available, environmental data from remote sensing satellites, from sensors, but also data from other spheres as well, such as economic data, behavioral data, and we really do need to find a way to bring that data together, to integrate it across multiple platforms, on multiple spatial scales, temporal scales, different uncertainties and biases. And if we can do that, we've got an exceptional opportunity to transform our understanding of the complex interactions between the environment, climate, natural ecosystems, human, social and economic systems. And the Joint Centre for Excellence in Environmental Intelligence, of which you've heard some remarks in the opening presentations, is a joint venture between the University of Exeter and the Met Office, and it's designed to perform research right at the interface of environmental and sustainability research, data science, artificial intelligence and digital technologies, and really bringing together 3 themes as described by Sir Adrian: kind of research, development and application, those core AI, data science techniques, and developing the algorithms we need to bring data together so that we can answer questions and provide the evidence base that is needed to support policy changes, behavioral changes, and other ways that we're going to find to enhance our resilience to a changing climate and the environment. Secondly is this infrastructure and data engineering research. Given those algorithms, given those data sets, how do we actually develop the platforms and the computational implementations so that we can actually implement the algorithms and actually produce outputs in a form that are useful for a range of users and stakeholders, and outputs in a form that are decision ready in some sense. And the third, drawing upon again some of the themes mentioned by Sir Adrian, Penny and Lisa, is capacity building and skills development. We know that we need to train a new generation of researchers, business people and policymakers with the ability to understand how AI can be used, and as Adrian described, how it possibly shouldn't be used, and how we can utilize it to its full extent to find solutions to these really very important challenges associated with environmental and climatic change. So I hope you'll enjoy the next 2 days of the conference. We have a fairly packed schedule this afternoon and tomorrow morning. This is a summary of this afternoon's schedule. If anybody would like to see the schedule in more detail, there's a web link at the top, www.exeter.ac.uk .com/IDSAI, which is the Institute for Data Science and Artificial Intelligence, /JCEEI conference/program. And after this introduction from Kirstine and myself, we'll kick off with a presentation by Professor Gideon Henderson, the Chief Scientific Advisor for the Department of Environmental, Food and Rural Affairs. And Gideon's presentation is entitled Data for Environmental Stewardship. Then we'll have a break, and we have scheduled a number of breaks throughout the day to allow you to go and get recaffeinated or to get some fresh air. Hopefully it's a sunny day where you are. The break will be followed by a presentation from Professor Nick Jennings, the Vice Provost, Research and Enterprise at Imperial College London, and then Professor Wilco Hazelager, who's Dean of Faculty of Geosciences at Utrecht University. We'll then have another break and then rejoin for a presentation by Professor Elizabeth Barnes from Colorado State University. And then we'll have our first interactive panel session led by Professor Stephen Belcher, Chief Scientist of the Met Office, together with the presenters from this afternoon, and they'll be able to answer your questions. So how do you pose those questions? Well, if you can use the chat facility, those questions will be collated and passed to Stephen, who will then ask them to the presenters. The chat facility is really one of your best friends, hopefully not your real best friend, for asking questions, but also if you have any issues, any difficulties with connections or accessing different presentations, please just drop a line in the chat and we'll get back to you as soon as possible. If you're having real problems and you've actually your connection has failed and you can't get back into the presentation system, you can email research events at Exeter. That's research-events@exeter.ac.uk, and they will provide you details of how you can rejoin the presentation and the conference system. Also, if you have any other questions, hopefully they can be asked by looking at the website www.exeter.ac.uk/JCEEI conference. And there you'll find a copy of the program, and you can also re-register for the event if by some amazing way you've managed to unregister yourself. There's also some further details of the Joint Centre itself and an email address in case you want to contact us for more details of the Joint Centre, or indeed how you might work with us in the future. And so with that, I think it's time for another short break before Professor Gideon Henderson's presentation. That break should be long enough, hopefully, for you to get a cup of tea, a cup of coffee, or some fresh air. And we'll see you back here for Professor Henderson's presentation in approximately 14 minutes. Thank you.
One of the problems with a pre-record like this one is you're never quite sure what the speakers either side of you are going to say. But I'm pretty sure that I'm going to be sharing thoughts with you today that are a little different from the speakers in this session. I'm not a computer scientist. I don't typically use artificial intelligence or big data approaches in my research, but I am an environmental scientist. And I think like any environmental scientist, I'm dependent on data and I'm dependent on the intelligent use of that environmental data. I should introduce myself. I'm Gideon Henderson. I'm currently the Chief Scientific Advisor at the Department for Environment, Food and Rural Affairs, one of the government departments. I'd like to start this talk with the document you see on the screen now, the 25-year Environment Plan. This was published in January 2018, about 18 months before I started at DEFRA as CSA. And it lays out a vision for where the government would like to take the UK landscape and environment over the coming decades. If we look at the headline goals of the 25-year Environment Plan, they're laid out on this text-heavy slide here. If we walk through the top 6 items here, they're things that everyone could agree are desirable from our environment: clean air, clean water, a thriving biodiverse wildlife, reduced risk from flooding and drought, good use of resources, and positive human engagement with our environment. These are all goals that I'm sure we would like to see realised, but just putting them in a document like the 25-year environment plan is not enough to make them actually happen. What you need to do as a government is to take them forward through legislation to see that you have some action in this area. So building on the 25-year environment plan, we're now pursuing the Environment Bill. I think most scientists, and many scientists, don't normally look at governmental bills. So here's an example of one, the front page of the Environment Bill, which is currently working its way through the UK government. It started in the Commons. It's now at report stage, which means it's been through committee stage. It's awaiting its third and final reading before moving to the Lords. And even on the front page of what is a document running to more than 250 pages, you can see some of the goals of this Environment Bill that are going to be set down in law quite soon. These include the setting and the monitoring of targets, which we must therefore meet according to UK law in the future. And these targets are going to need to be set by 2022 and then met in the years subsequent. Now, clearly, the setting and the meeting of targets is going to be absolutely dependent on data, environmental data, and on our understanding of how we can manage the environment to improve outcomes as measured by that data. Now, the targets that will be set by the Environment Bill are required to be at least in 4 areas. These are in the areas of air quality, biodiversity, water, resource, and waste. And there's also a requirement for a particular particulate matter target in the air as well. And this rather nice picture here demonstrates how these targets might help us to improve the environment, thinking about the cleanliness of the water, the biodiversity of the ecosystem around the water, and a rather cleaner, you'd hope, bank of the river in the future without quite so much scattered waste as that. The Environment Bill will create a new statutory cycle by which we'll have to make sure that we monitor, we collect the data, we plan, and we report that data going into the future. Now, DEFRA as a department already collects a great deal of data which can feed into that process. Some of this data collection is done in our public sector research establishments. Those are listed here. The Environment Agency, of course, is a large one, but there are others, Natural England, the CFAS, which looks at fisheries. We look at animal plant health. We have the Royal Botanical Gardens at Kew, Forest Research, and others. And some of the other agencies also collect substantial amounts of data. Now, one thing that I think is important to point out to audiences that are less familiar with this sort of ground-based data collected by people in the field is that it's often not actually very well architected. It's not brought together. We don't have the data in a good format that we can start to apply big data approaches to this. And that's one of the challenges we face, is really to get this data together. All these agencies have substantive data sets, collect substantive data sets, but they're often being used in a day-to-day process in that agency, not brought together into a system where we can use them to be cleverer about the stewardship of our environment. Now, if we want to be cleverer with the stewardship and we want to collect new data to help us meet the targets, we are dependent on money in the same way that academic researchers are dependent on the success of their grants to achieve their research outputs. So here's a picture. I like to think this is Rishi actually thinking about DEFRA's budget in the future. Probably not, but the good news is that he and others at Treasury did decide in the recently completed spending review that DEFRA should have some award in its R&D budget for 2 areas that are directly relevant here. One of which is money for a data science hub, specifically to tackle that challenge of bringing together all that diverse data from our different agencies and making it accessible, putting it into an architecture where we can use it for cleverer approaches. And the other lump of money that we got specifically in this area was for natural capital and ecosystem assessment, a program to map out what the environment looks like in the UK. Let me share with you a couple of slides from that program, from the team that are running that NCEEI program, to give you a sense of what that program will do and the type of data that it will get. I'll just read out some of this text. That NCEEI is a comprehensive and long-term program. It actually initiated this year and will continue next year and beyond. It's going to transform landscape decision-making in England by providing a really rich picture of the state of our environment, both on land and at sea, and by going on into the future, how they will change. So it will collect the data, it will assess the data, and critically, it'll make it widely available for people to use. So this process, coupled with the data hub, will make data from DEFRA sources expand and also much more widely available for people to use across the community to apply some of the big data approaches that others in this session are talking about, and to learn much more about the environment. The data that NCEEI will collect will be done in several different ways that are summarized here, including techniques like citizen science, using and mobilizing people who are interested in the environment, gathering the data that we already have, and using some of the other DEFRA programs such as environmental land management to bring data together into this architecture. And as I said before, this will happen both on land, collecting critical biodiversity and carbon and water data, but also at sea, thinking about biodiversity in the marine setting, thinking about different geographies on land and at sea, thinking about how we can bring them into maps and use them as data sets to realize lots of our goals, and I hope lots of research goals as well. Now, one source of data that we'll use here is satellite data. This is clearly a valuable data resource, often one that's already in quite good shape in terms of its architecture. This is an area where DEFRA leads in many aspects for UK government. And I want to now just do a little brief interlude to show how we can use some of the data that we collect in DEFRA, including satellite data, to compare not only across different bits of DEFRA, but also into other sectors of government and into other challenges. So here I want to make a little bit of an interlude into two areas that have dominated this year, certainly in government, and I think for everyone: the C word and the B word. And the C, no, it's not for Christmas today, although that is coming and I'm sure we're all looking forward to it. The COVID year that we've been through has demonstrated to us how we impact with the environment and interact with the environment. I'm going to use an example here, which many of you may have seen already or something like it. This is actually from China, although you can see similar things elsewhere. And this demonstrates the use of data from space, satellite data, to map out air pollution. We can see how substantially that's changed through this year. So let's hope this works. Here we go. This is running from just before lockdown. And as you go through lockdown in China, going through February, you see this substantial reduction in NO2 in the atmosphere over China, reflecting the change of human activity in that area. So you might be wondering what the B word is if you haven't worked it out already. This is Brexit, of course. Any week now we're due to transition in some shape or form from the EU. And this has been a challenge that DEFRA have also been facing up to, particularly through the Copernicus programme, making sure that we continue to have ready access to Copernicus data beyond the 1st of January, and hopefully also involvement in the Copernicus programme itself. And of course, the data that you see, that NO2 data you saw before, is valuable satellite data, in that case from the Copernicus Sentinel programme. And one of the reasons to show you COVID and Brexit-related air quality work here is that the environment, of course, interacts substantially with human health as well, positively by our getting out into green space, but also negatively through the pollution that we experience in the air. One of the pieces that DEFRA, one of the pieces of work and research that DEFRA's been involved in recent months has been really to try and work out whether the air quality that we have in quite bad levels in some of our cities in the UK is being responsible for an increase of deaths in those areas. Quite worrying data was coming out of the States in the early days of the outbreak, demonstrating really quite a strong correlation between bad air and people dying of COVID. We wanted to look at that with UK data so we could compare our air quality data with the data that we have from other departments, particularly from the Department of Health. This rather complicated graph here, which I'll just talk you through, demonstrates that as you go through the outbreak in the UK, from pre-outbreak towards the end of the first period of lockdown and the first wave, it shows you on the top figure here the correlation that you see between air quality and mortality from COVID. And you can see quite a strong correlation early on between NO2 in the blue or PM2.5, the particulate mass, in the green here. As you go further through the outbreak, though, that correlation falls away and becomes much less significant and less acute as we go towards the end of the first wave. And this demonstrates that actually the initial relationship between human health and between pollution in this setting was driven largely by coincidence. It was driven by the fact that the people with the cases coming into the UK were coming into densely populated areas where the virus was spreading, people were dying, and those densely populated areas were also often those which were heavily polluted, which drove the correlation rather than there being an actual direct relationship between bad air quality and excess mortality in those areas. So a powerful example here of how, if you've got data in an accessible form, you can use it to learn more about the processes, not only in the environment, but more broadly as well. So I've taken you on a bit of a journey so far in this talk, because we've been building off the 25-year environment plan. And I ran through some of the areas that are above the line here, the top 6 items in the environment plan. One thing that's surprising, I think, when you look back at this document, published, as I said, in January 2018, is that in those top 6 items, there's no climate. Climate isn't mentioned up there. It's only when you get further down the list of goals that you see climate mitigation and adaptation featuring here, and it's couched in those terms, in terms of making sure that we don't damage the environment by climate change. Now, in the time since then, I think that the view about the importance of climate change has really grown significantly. Of course, we were concerned before, but I think we've become much more concerned in really quite recent years about the damage that climate change is incurring on the planet and our need to do something about it. So if I take you forward to June 2019, only 18 months after the Environment Bill, that awareness of climate change had risen sufficiently that you see Chris Skidmore here, the government minister, signing into law the requirement for the UK to reach net zero by 2050. This was a big change in our perception of how rapidly and urgently we needed to deal with climate change. And of course, this is also a challenge where environmental data and intelligent use of that data is really important. I should stop and just be proud, I suppose. And this is a sense of pride that I had before I was a civil servant about UK leadership in this area. Of course, it's right that we should keep pushing the government to respond ever quicker and more urgently to climate change. But we were in 2008 the first country to really legislate for a requirement to reduce CO2, and the net zero requirement. We were the first major government to act in that way as well. Now followed by many others, including, of course, most recently China, which is a very significant step in a positive direction. All sectors of society are going to need to respond very substantially to the challenge of net zero. One of the striking examples of that, I think, is around electrification of transport. The announcements made by government recently that we're going to have to move towards the banning of new petrol cars after 2030 means that we're going to have to move from a 7% penetration to a 100% penetration of electric vehicles in a 9-year period. It's a really incredible change with all the required infrastructure that will be built as a consequence and the loss of tax revenue from sale. Now, DEFRA's challenges will be equally large. We're going to have to respond at large scale as well. And I wanted to just highlight, I'm not going to go into too much detail, although I could easily, this is a subject close to my heart, so I could talk for a long time about this, but I wanted to just raise 4 particular areas where we're going to need data and thinking extensively about carbon emissions in DEFRA's space. And these are all related to our use of land. Each of these images reflects a part of our land use which is responsible for at least 10 million tonnes of CO2 emission or equivalent gases every year. And we're going to need to see response in all of them. Trees, of course, we're already acting to grow many thousands of hectares of trees to capture more carbon. Nice example here from Whiteton Woods, just outside Oxford where I live. Livestock, similarly, this is responsible for large amounts of CO2, actually methane emission. More than half of our greenhouse gas emissions come from cows and sheep. We also need to think about peatland emission. Peat is decaying because it's often dry, and that emission of carbon is currently not accounted for in international accounting for carbon, but will be in the near future. At that point, overnight, the UK's emissions will go up by 20 million tonnes of CO2 a year. We're going to have to do something to re-wet our peatland, a really substantive change to the way that we manage our land, including some of our most productive farmland. And the 4th area here is biomass, intentional growth of material that we can burn as a way of generating energy and displacing coal and perhaps burying carbon underground. So these are areas where we're going to have to act, we're going to have research, and we're going to have to collect data to understand how we have acted and the consequences of legislation and action. And I wanted to just share one of the ways that we might think about learning about our carbon emissions, a technique which I think is a fantastic way of studying the surface of the Earth, which may not be, some of you in the audience may not be fully aware of, and that's eddy covariance. This idea that we have the technology to measure at multiple times a second, both the movement of air and the movement of gases like CO2. And by coupling those measurements together, we can learn in very real time about fluxes of greenhouse gases, of methane and carbon dioxide in and out of the environment. This approach has been applied in many terrestrial settings. And here's a nice example from Illinois in the States, looking at biomass, looking at how much carbon is sucked into biomass over a multiple period of years here, with the green curve on here representing how much is being incorporated by plant growth, the red showing you how much is respiring, how much carbon dioxide is going back into the atmosphere, and the blue therefore showing you how much carbon is captured each growing season into the soil or into the biomass through time. And these sorts of measurements, these sensing and measurement technologies will complement those that we have from direct observations of things like biodiversity or tree growth and satellite observations to give us this rich tapestry of data which we can use to understand our carbon cycle as we move towards net zero in the future. Now, one of the challenges when you think about land use is that if you tackle one bit on its own, it often has consequences on other things that you're trying to achieve. And this rather nice image here, this heat map put together by the systems research team in DEFRA, demonstrates some of the complexity that we get when we start to interact in this way. Down one side here, down the y-axis, we see some different interactions that we might pursue in order to reduce carbon dioxide emissions, reduce greenhouse gas emissions. And then on the other axis, you see the impact that that might have, with green being good and red being bad, on other aspects of our environmental management. Without going into any of the details on this image, I think it powerfully makes the point here that we need to think about our environment as a system. We need to get the data into a format where we can look at the interactions, we can think about how changing one thing will change many other aspects of our environment. We need to map out and be quantitative about the way that systems interact. I think I'm out of time here. I'll leave you with that systems point, but I do want to make one more point to those in the audience who perhaps are students or otherwise thinking about some sort of career change, and that's just to encourage you to think about the civil service and think about science in the context of the civil service as you're doing that. I might just flag up one way in to that, which is through the FAST stream, particularly the science and engineering FAST stream. But there are many challenging jobs in the civil service where you can bring environmental science and data skills really into the policy interface and use them extremely profitably. So I encourage you to have a think about that. So thanks very much for listening. I'm going to leave you now and look forward to the panel discussion that comes in a little while this afternoon. And I'm going to leave you here with a rather scientific view of the Midwinter Festival. We're all approaching the Midwinter Festival, and no matter what your faith or belief system, what we're celebrating very shortly is the fact that we've got we're about to reach the minimum of daylight, as shown by very scientific images like this. So for me, happy Christmas, and I wish you that, or happy holidays in whatever form you take them, and look forward to the panel discussion soon.
Hello, my name's Nick Jennings and I'm the Vice Provost for Research and Enterprise at Imperial College London. I'm also a Professor of Artificial Intelligence there. What I want to talk to you today about is environmental intelligence and how it combines in a synergistic way with artificial intelligence, and how this combination can work together to help us build exciting new applications and really make advances in new forms of science. So environmental intelligence sits at the boundaries of environmental and sustainability research, digital technologies, AI and data science, really bringing these areas together in a closely coupled way. It's very much driven by the increasing availability of large and complex data sets from diverse sources, and this presents us with an exceptional opportunity to transform our understanding of environmental change. It's going to be crucial as an area in ensuring that we have the data and information required to tackle global grand challenges, such as clean growth, the creation of sustainable cities, and mobility and facilitating movement of people freely, safely, and with minimal negative impact. An example of where this technology and this area might go, I think, is given by Virtual Singapore. So Virtual Singapore is a digital twin of Singapore. It includes typical map and land data, and the platform also incorporates other real-time dynamics as well as information about demographics, climate or traffic, making it a tool that offers enormous potential and which can be used in many different ways. Virtual Singapore will enable public agencies, academics and the research community, the private sector and also community at large to make use of the best information and system capabilities for policy and business analysis, decision making, test bedding of ideas, community collaboration and other activities that require information. It really is, I think, an excellent example of how these technologies can come together and really give us an exciting and compelling vision for the future. So artificial intelligence, the field that I've spent my career studying, really underpins this endeavour in environmental intelligence. AI and machine learning are increasingly embedded in all forms of research and innovation. And I think AI will have a number of advantages and facilitate a number of advances in this area for a number of reasons. Firstly, it involves the analysis of huge data sets and really lets us understand what we have at present, help us predict what our future events are likely to be, and create new products and services that can help minimize our negative human impact and optimize how we interact with our environment. It enables data-driven planning and a whole systems approach to environmental innovations. So AI, as I've said, is an underpinning technology. It can be used across a wide variety of applications. And here I'm just going to talk about a few that are, I think, relevant, or perhaps most relevant to the area of environmental intelligence. So in the energy domain, AI can enhance the predictability of demand and supply for renewables across a distributed grid. It can help improve energy storage efficiency and load management. It can assist in the integration of renewables and enable dynamic pricing and trading, creating market incentives. And I'm going to come back and say a bit more about some energy applications later on in this talk. It can help with climate change, so AI can help provide us tools to monitor air pollution in real time. These tools can help identify sources of air pollution quickly and accurately, such that we're able to respond to them. AI can help in urban development, again sort of providing real-time citywide data on energy, water consumption and availability, traffic flows, people flows and weather, and really help construct a model of what's going on now in an urban environment, such that it can be monitored and interventions can happen on a short and real-time basis. It can help with our oceans, so machine learning can help us assess the changing conditions that harm the oceans, such as illegal fishing, discharging industrial effluents into water bodies, and illegal solid waste disposal by local people. In terms of agriculture and food, AI can help us with the detection of crop diseases, to help us provide timed nutrition to livestock, and generally optimize agricultural inputs and returns based on demands and supply. AI can analyze simulations and real-time data of weather events and disasters in a region to seek out vulnerabilities and enhance disaster preparation, provide early warning and disaster response prioritization through the coordination of emergency information capabilities. And again, this is an example domain I'm going to come back to later. In terms of transport, AI can help us route and manage traffic optimization. It can help with eco-driving algorithms for our cars, and it can help us in the future with platooning of cars to traffic so that we can work in the most energy efficient manner, and also help with autonomous ride-sharing services. So AI really can help us with a wide variety of these areas, and I'm going to pick on a few of these areas and drill into them in a bit more detail in what follows in the rest of this talk. So what I'm going to do is I'm going to illustrate these potentials at a bit more detail with some examples that mainly come from colleagues at Imperial College London. So the first big area that I think is very important in terms of environmental intelligence is the visualization of data. So at Imperial we have a global data observatory that enables the visualization of data in a way that uncovers new insight, improves the communication of complex data sets and analysis in a multi-dimensional environment. So as you can see, there's a picture here of a room. Each of the squares that you might be able to see is a large-scale television, and so what it is a room where you can really go in and explore the data. It is fully immersive in terms of being all around you, and that scale and that fidelity at which you could see that data is really important to understand and observe new patterns in a way that you can't observe patterns when you're just looking at it through one screen or through a very narrow lens. So sort of the way in which it surrounds you is really important to it. So the visualization that we have here, amongst the many that we have in our visualization suite, is of the Shanghai Metro. So it shows the Shanghai Metro stations, shows their live data throughout the day, taking data from how many people were coming in and out of stations as its basic inputs. And then we can use this data to construct models of passenger flows and crowd management. And this is real value in helping us manage city transportation, helping to ensure that the flows of people happen efficiently, safely and securely. And what this can model is, if you're going to have some planned maintenance, or you want to shut particular stations or particular lines, it can run what-if simulations of how the rest of the network will be impacted by these changes. And also in an unplanned situation, you can try and get ahead of events and run simulations as to where crowds are likely to occur, where blockages are likely to occur, so that you can construct and send your resources there in a proactive way. Another example is around some work that we're doing around air pollution. And here we're sort of using advanced computational techniques, so computational fluid dynamics, to simulate what happens at particular places. And so this particular model is what happens at bus stops, but we've done similar modeling for what happens in buildings and on the wider city scale. And what this does, what we've done in this work, is to develop a highly complex model that requires supercomputers to process huge amounts of data. And here we're using AI not just to process that data, but to speed up the whole process of these simulations, of these calculations, by several orders of magnitudes. And without AI, this execution time would simply be too high. So as well as processing the data, which is what you'd expect AI to do, actually we're using AI in the simulation and the modeling aspect here to construct models at a scale that we've not been able to do previously, because we're using AI methods and heuristics in order to speed these things up. So once you have models at this, once you have granular models of particular areas or particular buildings or particular rooms in particular buildings, what we can use them for is to reduce the impact of air pollution. And in this particular case, the air pollution produced by buses. Because what it lets us do is help us improve our routes to try and avoid busy junctions. It can help us optimize our timetables and bus frequencies, and also helps with the strategic positioning of bus stops to limit the negative impact of passenger waiting time. Again, an example of data, model and computation coming forward to help give us some intelligence about the environment in order to figure out what needs to happen at what points. Building upon this, this is work that we've specifically done around COVID-19, where we've taken the same base technologies, the same underpinning modeling technologies, and used it to show how the virus can spread through coughing and sneezing in classrooms. In this particular case, it's obviously a particular concern to us as a universities, but also what you can do is you can apply these same techniques into trains and to shops to really understand how that virus can spread. And again, it's having a core model and being able to run it at high fidelity and at decent speeds in order to get these kinds of results. So our final example that I want to talk about in the environmental space is work that we have going on in our Leverhulme Centre for Wildfires, the Environment and Society. Now, this was set up in 2019 and is led by Imperial in partnership with King's College London, Royal Holloway and Reading. And it's the first centre in the world to address wildfire challenges from a global perspective. It brings together physical and social scientists to help understand the factors that influence fire and provide guidelines on successful fire management. Research in the centre falls under 4 strands which focus on major topics or regions of interest around the world. So firstly, the first theme is fire in the north. Here we have projects studying changing fire regimes in northern regions, the socio-political causes and implications of such changes and their effects on global carbon budgets and climate change. One specific project is creating a regional model for the study of air quality degradation from wildfire emissions. The second major strand is around fire in the tropics. Here we have a number of projects that aim to develop novel methods to study the diverse drivers and impacts of wildfires in specific tropical regions. One example project aims to create landscape scale agent-based modelling of anthropogenic fire for case study locations, such as in the Mediterranean basin or in tropical Africa, and develop methods to ensure the results apply at broader scales. The third area is in fire in global systems. As we're all aware, regional differences in the environmental, ecological, economic and policy context of fires are exceedingly important, but ultimately we have to be able to understand them in a global context. And so an example project in this area is looking to devise a simplified generic version of the fire spread algorithm that can be used operationally, that is being used operationally in the US and other fire services and embedded in a number of global fire models. And then the final strand that the centre is looking at is fire at the wildland-urban interface. So that piece where they come together and mix for the first time. So here we've got projects exploring case studies linking the physical reality to the social and institutional context of land use and fire management, aimed to tease out the causes of wildfire risk, as well as to understand the optimum ways of managing wildfires at different interface contexts. And here a specific project involves economic modelling that aims to state and reveal preference valuation techniques and combines that with individual level data from large social, time use and economic surveys, combine it with aggregate economic data, land use, meteorological and earth observation data in order to really try and quantify the impact of wildfires on human welfare. So this is a great example, I think, of the kind of area and the kind of work that's really central to environmental intelligence, bringing people together from diverse sets of backgrounds to tackle really important global challenges. And I would commend the Centre and their work to you. So I've spent a bit of time giving some environmental examples. What I now want to do is to give some examples that come from a second major area where we have expertise and work going on at Imperial, and that's in the broad area of energy and digitalizing energy. So we have a global challenge institute at Imperial that brings together people from around college, from all of our faculties, which is the Energy Futures Lab. And what they're very much concerned with is the key technologies that underpin the digitization of energy and its impacts on society at large, society and the environment. They've explored the use of big data analytics for use in electricity transmission and distribution networks to help improve reliability and in consumer usage for demand response purposes. Here they've used AI and machine learning within the energy system, which will inevitably move from a centralized to a decentralized model, with the number of assets, the number of providers and consumers rapidly increasing. So here what's happening is they're using AI to help in a number of different aspects. So in modeling and optimizations, in exploring markets and investments, in terms of looking at maintenance and security, and in terms of those customer-facing services. So a specific example of one of these projects is on renewables.ninja, and this is an open platform developed by colleagues at Imperial. The image up here shows what the platform looks like to users, and you can see the URL up on the screen. So this platform allows the simulation of hourly power output from wind and solar plants located anywhere in the world. The platform combines sources of wind speed and solar irradiance data from NASA and EU SARA with PV and wind output simulation algorithms that the authors have written. Users can select a specific point on a global map and run a simulation of solar or wind output, choosing values for capacity, positioning, and for wind turbines. The daily mean output and monthly capacity factor are then simulated, allowing users to understand the optimal positioning and sizing of renewable technologies for a given area. So it really helps policymakers, people who want to invest in these renewable technologies, to help position where they should put their resources. And the next example in this space is about empowering humans. So with residents, even in the poorest parts of the world, now owning mobile phones, colleagues from the Department of Civil Engineering have created the Network Water mobile app for people to record the timeliness, quantity and quality of their water. And this is a particular application that's running in Kathmandu. Here participants send photos of the results of water quality tests to the Networking Water Facebook page. And what they receive back is personalized feedback on the results, including recommendations of what action they should take to use the water safely. So this crowdsourcing application, using people and artificial intelligence together, has a number of distinct purposes. So what it can be used by is the Kathmandu's Valley Water Utility to help monitor the water distribution and take actions as needed. It can help development partners and funders to better evaluate the impact of their investments, and it lets residents be involved in improving their water situation. Finally, I'm going to end up with an example that I was personally involved with, and this is about, again, combining AI systems together with the best of people in order to get the best of both worlds. So in a project that I led called Orchid, we looked at a disaster response after the Nepal earthquake, and what we used was we combined satellite data with crowdsourced data to determine the best placement of water filters, again as it happens around Kathmandu. Here we used AI to analyse huge volumes of data to identify potential casualties and detect areas of needs. And so what we had was the AI focusing on things that it's good at, analysing huge volumes of data. And what the humans added was trusted observations of the situation and understanding of the broader context in order to help inform the disaster response. So I've skipped through, presented a number of applications. I could have presented many more. This is a really exciting and rich area, this combination of artificial intelligence and environmental intelligence. But where I wanted to finish up with is some of the significant research challenges that are still to be tackled in this area. And so here I start with 4. So the first of these is the development and sharing of high quality data and models. This area, like so many areas of artificial intelligence, requires the efficient and secure sharing of data between scientists, businesses and governments. It also requires complex models to be made available of particular phenomena. And so the emerging area of digital twins and simulations of environments and of cities and of individual behaviours is really important in this area. So that's starting to happen, but there's still plenty of work to go. The second area where there's still significant work to go is around visualization of complex data sets and models. And you will have seen the example that I gave around the Imperial Data Observatory. This is just one instance of the next generation around the next generation of visualization technologies. It's really important when you're looking at complex data sets that you find ways and means to really understand what's involved in the data, why it's behaving in a particular way, in order to derive those new insights and analytics. And I firmly believe that visualization is central to that. The third area which I've touched upon is that AI methods enable humans and advanced software to work together in partnership. And so the example that I gave around the work of the ORCID project, I think is a really strong example of how you can get the best out of the humans, providing what humans are good at, combined with what the best that machines are good at, in order to get something that's more than the sum of those parts. And so I'm very much interested in the area of human and AI partnerships, really working and cooperating together. And then the final research challenge that I want to talk about is bringing together people who have distinct expertise in order to tackle these problems. So as an AI scientist, I've worked with people from a whole variety of backgrounds and disciplines in my career, and that's been a real joy and a fantastic opportunity to really learn about other disciplines and other areas. And this is absolutely central to what's going to happen in the area of environmental intelligence. It requires a number of different disciplinary backgrounds to come together to tackle these really important challenges for us as a society. Thank you very much.
Good afternoon. My name is Wilco Hazeleger, and it's a privilege to talk to you today about data-driven environmental scientists. I've worked with quite a few of you in the audience, I think, at the Met Office at the University of Exeter on traditional methods of weather and climate prediction, mostly with numerical models. Today I want to talk to you about some, well, perhaps more novel developments on the use of data science, of AI, and give some examples of it, and perhaps at the end an outlook on where this field is going. We have to do this from remote. I'm at my working room here upstairs in my house in Utrecht, but I guess this is the way we work right now. I'm in good health. I hope you as well, and that we'll enjoy a nice afternoon with presentations and discussions. Let me start with a picture that sort of makes the point that I will make at the end as well. It shows a photograph of an event, an extreme event, just a few months ago in the Southern Alps, where heavy rainfall and flooding caused a lot of damage and casualties. And if you look at this particular picture, you can see the complexity of such an event. It's not only the weather or not even only the flooding, but also its infrastructure, both the roadworks and the wiring that you see here, and the emergency management trying to do their work really well, and the social media at the same time. Well, this whole complexity, to deal with that, to understand what goes on with extremes in climate and weather, basically such a picture as this shows that it's much more complex than just the weather, what we normally deal with. And that makes me think of perhaps a plot like this, or a figure like this, which was made by Alexander von Humboldt, a great German geographer, over a century ago, when he went to the Andes and tried to understand what was going on in that environment. And he noted that the traditional reductionistic approach, which mostly comes from physics and which brings us very far, actually wasn't enough for the issue that he was and the themes that he saw there. And he was proposing a much more holistic approach where different pieces of information and data comes together. Actually, he also saw already the human impact on the environment, in particular with land use change. And this sort of relates to my story as well. We normally, in a traditional climate and weather modeling side, take a more reductionistic approach, starting from first principles. But given the amount of data around us, perhaps a more data-driven approach is also very, very suited. So, like I said, this is what we normally do. We have equations of motion, and they look a bit like this. In our case, often the primitive equations, which is derived from the Navier-Stokes equations. And we compute these equations on a grid. And that grid we refine and refine to get more and more detail in that. And that has brought us very far. Just as an example that this can work, and works actually really well, on the right-hand side you see the wind field from a climate model, which works on a grid of about 100 by 100 kilometers, a bit more. And on the left-hand side, there's the very same wind field computed by the very same model, but then on a finer grid of about 25 by 25 kilometers. And you can already see these red dots there, which are hurricanes, the most damaging features in terms of weather on our planet. And you cannot simulate these with these traditional climate models, but enhancing the resolution apparently works because we can more accurately and more reliably simulate these with new generation of models. And there's a background to this. If you take, and this is my most complex figure, I think, if you look at the spectrum of kinetic energy in the atmosphere as a function of wave number, and that's on the left-hand side, and if you follow just a blue line, then that spectrum is continuous. And at a certain point, the dashed line goes down. And that's a coarse resolution result, and you see that basically the energy is dissipated at quite large scales. The fine resolution model, which is the continuous model, the high resolution model keeps to continue and also falls down at some point, which means likely we need even finer resolution. The relevance is even more if you look at plots like here on the right-hand side, which shows the same energy transfer, or the same energy, kinetic energy, but then transferred from one wave number to the other. And this feature on the diagonal basically means it takes energy from larger waves and it puts it in smaller waves or smaller wavelengths. So this is downscale transfer of energy. That makes sense, right? The energy comes in from the sun at very large scales, at a planetary scale, and then at the end is dissipated at a very small scale. But you also see a feature here at the bottom where energy from smaller scales is fed into larger scales. And this upscale transfer is a particular feature of our flow of geophysical turbulence on the planet that we have. And that means that it's useful to go to very high resolutions, in particular to simulate things like blocking associated with droughts and heat waves and mid-latitude storms. The other direction, what we do in traditional field of climate and weather modeling, is just enhancing complexity, because we see the relevance of coupling different subsystems together. whether it's atmospheric chemistry, or whether it's the land surface, or sea ice, or even socioeconomic systems. We tend to couple more systems because we see that it really interacts, just like Van Humboldt said. But there are pretty big challenges in this sort of traditional route that we follow. The first challenge is computationally we're hitting limits. And that's because enhancing resolution on these climate and weather models in a spatial sense mostly means you do this in at least 2 dimensions and perhaps 3 dimensions. That means that the computational cost goes up by a power of 2, and actually if you take the time stepping into account, a power of 3 as well. So basically it becomes very, very costly in computational times, but also the wall clock time to complete a simulation becomes too long. And although we're making advances from year to year still in computing, up to exascale computing right now, we sort of see the limits of this. So where does the field really go after that? Another limit is that despite the higher resolution that we obtain by doing this, and perhaps the more complexity, the uncertainties reduce on a very large scale, but they don't reduce on the smaller scale. This is an example from just rainfall in the Rhine catchment basin. And if you look at the area around Switzerland, it's very blurry in a coarse resolution model. It actually has a lot more detail in a finer resolution model, but that detail is different than what you get from the observations, which in this case was put on the same resolution as this fine resolution model. And for sure, this kind of data is still not enough to feed into models trying to forecast and predict the flooding issues that you previously saw, which basically means we're still far away from that, and perhaps we need other kind of methods as well. And that's where the theme of today's conference comes in, and the discussions that we have. Can we use more data-driven techniques in our kind of field, and where does that bring us? Well, let me first take a little step back. Where does this all come from? Well, there's a very nice book edited by Tony Hay called The Fourth Paradigm, which sort of structures the scientific evolution around a few eras. And the first one is more where theory and experiment was developed. And it started in antiquity with people like Aristotle, up to the Enlightenment with, well, the well-known great scientists that we had, like Newton and Galileo and others. And actually, if you look at the previous century, something new came around, which was computing, simulation. We don't do the empirical work only in a lab, really to test our theories. We add to this the ability of computational systems to simulate the world around us. And this is a different way of approaching science, which was added to the traditional way. And then in the current millennium, we see a new development again, back to perhaps empiricism, where we see that lots and lots of data is available. And that data actually tells us already and can constrain the reality that we see around us. And can we use all that knowledge to actually predict? Some people went as far to say it's the end of theory. Well, I think by now we see that's not true. We may see a nice convergence of all these different elements that you see on this slide. And we see this coming back in our fields as well. And these are just some examples on projects that I've been involved in myself. The quick wins have been done when it comes to data-driven science. For instance, on the upper left-hand side, the amount of work that's being done on feature detection, basically pattern recognition kind of techniques. There's lots and lots of literature on it, and it's relevant, it works. Deep learning being used to do that, for instance, very much like your self-driving car. Or if you look at the top middle, time series forecasting, we started that already with deep learning quite a while ago, in the previous century. And now it's being advanced more and more with more data and more computational power available, and we use it quite a bit. Perhaps a bit more novel, staying to the traditional methods but speeding them up. And you can do that in different ways. For instance, speeding up the numerical solvers that we have in our systems. Then we still can adhere to the physical principles, but speed up the algorithms that we have to compute them. Similarly, on the bottom left, speeding up by replacing small-scale features in models like clouds, radiation, turbulence, with learned models. There's a lot of literature around that as well. And of course, there's still the promise on combining all the different kind of data in a kind of big data problem. Whether it's the physical data or data from satellites on the biological world, so vegetation, for instance, or even social media information. Can you combine all that data? And you can actually to get more information, learn from what happens at a very small scale, and perhaps even predict better. And perhaps the biggest challenge of all is to do the bottom right-hand side, where there is more and more literature about it. Can we actually learn physics? Can we learn the physical equations, not only solve them quickly, but can we replace the Navier-Stokes equations by a learned model? And for specific settings, there's quite a bit of literature around it already. And it's perhaps the upper end of the challenge that we have. Well, let me give you a few examples of how this can work. And first of all, can we learn, with deep learning, can we actually learn the weather and climate system? Does that work? And to do so, to test this with a student, I started off with just a very simple model. A very simple model of a climate system as proposed by Lawrence, which has all kind of elements in it, which mimics the climate system and the weather system. It's a model which mimics waves on a jet stream, and such waves are very relevant for our storms, our heat waves, our droughts. And you can describe such waves on a jet stream by just these coupled set of differential equations that you see here, with variable x, y, and z, with the different properties of those waves and of the jet stream. And it has parameters a and b, and it has a forcing, an external forcing F and G. And if you look at the solutions of this kind of system, which you cannot compute analytically, but you can do that numerically quite simply, for certain settings this is a chaotic system. So it depends, its solution depends on the initial conditions and very details of that. And that mimics very much how we look at weather prediction, which is very similar to that. The other part that's in this set of equations, it has parameters in it which are uncertain in themselves, and it has a forcing, and has an external forcing that's framed here as F and G. And that means it's very reminiscent of a climate model as well. So this kind of system we can play around with. It's a conceptual model, and see what deep learning brings us, and see whether we can apply that to a weather prediction problem or ensemble weather forecast, which is inherently probabilistic, or a climate projection where there are uncertainties in forcing and in parameters. So how do we go about to do that? We decided to use a neural network and an architecture of it which has been used more often, which is called long short-term memory neural network, which actually is suitable for systems that have a little bit of memory. Like any other neural networks, it couples all kinds of cells together, and these cells are coupled to each other through different functions which have weights going with them. So there are two things we really added to this system. One of them, we made sure it's convoluted, so that it's not only one cell, but it's a convolution of cell where you keep the information on the correlation, on the covariances between different layers that you convolute. And you could see this as air pressure, temperature, precipitation, coupled in a consistent manner. And that brings in physical consistency in the system. And the second thing we did is something which has been done quite recently in the machine learning and AI literature, is to bring in a Bayesian dimension to it. And we do this in the weights that are determined in these weighting functions to couple different fields. And we make these basically, these weights we replace by distributions of weights. And in that way, we can learn the stochastic character and perhaps even the uncertainties in parameters as well. And this makes the system perhaps suitable for weather and climate prediction. Let's see if that actually works. If we can predict the Lorentz model in this case, so X, Y, and Z, the previous slide, with this kind of system, and whether you beat perhaps a traditional ensemble prediction in the Lorentz system, and perhaps more challenging, do you learn the attractor of this system? And actually, if you just look at and we had to set this up in a specific way, there's too much detail to go into that here, but if you look at forecasts that we did, then it actually has properties like in a normal weather and climate prediction and projection. For instance, if we forecast 30 days ahead, then you see that it can typically follow the phase of a solution and the trajectory of it, and it has a certain band of uncertainty around it, which we can show is sort of similar as what you would expect from the Lorentz model itself. And if you make such a simulation longer for 3 months, there's still some information in there, but you're losing it. And after of these very long simulations, there is no actual information of the individual trajectory. But we could actually show that all these green lines, which are basically numerical or forecasts from the neural network, that all these forecasts follow the phase space on the attractor of the Lorentz model. Not perfectly, but actually pretty close, and it depends on the loss function that you include here, how good you want to do this. Of course, you want to avoid overfitting and issues like that, but we could show that we can keep the model physically consistent, and we can bring the workflow in and knowledge in a way that we can represent uncertainties in the way we think is physically relevant. And this is an example where we, in the end, applied the very same technique to Arctic sea ice forecasting. And you can see already a time series of forecasts through a seasonal cycle with less ice in the summer and more ice in the winter. And we could show that we can beat traditional sea ice forecasts with such a system. So it's promising. I won't say it's the panacea of everything, but this is promising. I now want to sketch at the end a much more bigger picture, a wider view on how these kind of techniques can be used. And this is something we explore in a new program of the European Union and European Committee coming up called Destination Earth, which is part of our digital future development. And what we want to do there is basically develop digital twins. Well, what are these? Digital twins are mirrors of reality. Basically, they are simulators that replicate reality as realistic as possible, constrained by real-time data. And those of you who are in weather forecasting think, hey, hang on, this sounds like a weather forecast. And that's true. A model is an abstraction of reality, but a very detailed and as much advanced model as we can get to is actually close to a digital twin. We try to replicate the atmosphere. On the top left, you see that as much as realistically as possible as we can. But we also want to do the right-hand side in a big, big detail. How do we do that? And that's where the development of the digital twins comes in. So we're thinking about setting up twins in a traditional sense, weather forecasts like you see here, where we have satellite data, all kind of other data coupled together with codes, and we try to simulate their constraint on the codes. It's a data simulation problem, but we want to do this in real time. But we want to go a step further, and the step further is that we're seeing the same kind of application for instance, forestry or in agriculture or in emergency management, where in real time we can interact with the data and with simulators to basically do robust decision making. And you can only do this if you use techniques from AI to do this in such a quick way with low latency. This is a huge challenge, but we're starting this right now. What it also takes is a very different computational architecture than we currently have. It takes a distributed architecture, but it probably also takes a cloud layer on top of it, where different kind of users, whether you're an expert user or an end user, can basically operate that system to either develop that system or to really produce what-if scenarios to base your decisions on, whether you're a farmer or whether you're doing water management in a country like where I live, or work in forestry or in energy science or whatsoever. So this is the view we have in front of us, where I think the field is going to, and where data-driven environmental sciences will be of big help and will develop much and much further. I thank you for your attention.
Pacific really pops out as an important region for the network's decision-making process. So for us in this example, the science is not really making the prediction. We can do that, and it's certainly important part of the process, but the exciting part is really identifying these predictable patterns or regimes of the Earth system that lend themselves to predictability. This is an example over seasonal timescales, but we've been doing this from subseasonal to decadal. Now, the second example I want to talk to you about is indicator patterns of forest change, in this case of climate change. So climate change in the 21st century can really be seen as a signal to noise problem. Here I've shown a plot that many of you have likely seen of the change in surface temperature between the end of the 21st century and the beginning of the 20th. Now, this particular figure was made by averaging over 29 different climate model simulations, averaging over 2 30-year chunks and taking the difference. And this is also using the historical and RCP 8.5 climate scenario. So what we see here is what many of us already know, which is red everywhere. That is, the temperatures are going up everywhere throughout these climate model simulations on average. The Arctic warming more than the rest of the globe on average as well, known as Arctic amplification. And this is a well-known fingerprint of climate change. What's hidden, though, in this image is uncertainty. And there are really two sources of uncertainty within this figure. The first is structural model uncertainty or model disagreement. That is, our models and our scientists were not quite sure how to best represent the physics of the real world in climate models. And in some cases, we don't know the physics in the first place. The second source of uncertainty is that of internal variability. Even if we had a nearly perfect climate model, we could never know exactly how the future would unfold due to, for example, chaos of the climate and Earth system. That is, any one year may not look like any other year purely because of climate noise, even without climate change or anthropogenic forcing. Now, of course, the problem here is this is all averaged out when I average over many climate models over many different decades. But of course, the real world isn't like this. We only have one real world. And so the big question as climate scientists is how can we tell which changes are the signal and which are the noise in our one observed Earth? That is, when we plot observed present day trends in temperature, how do we know which blobs are forced by anthropogenic sources and which are just due to, say, internal variability? So there are many scientists trying to attack this problem in many different ways. And here I want to tell you how we're using interpretable neural networks to do this. That is, what we do is we train a neural network to do something that may seem relatively silly. That is, we train the network to predict the year of a map from one of these climate model simulations. We input an annual mean map of surface temperatures from any year between 1920 and 2100. And we ask the network, which year did this come from? Now, to successfully perform this task, it turns out that the neural network must learn regional signals within that surface temperature map that are reliable indicators of the year. So let's see what happens. Does it work? So on the x-axis, I'm showing the actual year of the map we fed the network. And on the y-axis, I'm showing the predicted year, or the year the neural network has been trained to think it is. A few things to note. First of all, the colors show different climate model simulations where the gray is the training data, which you can't see because it's hiding underneath the colors. And the colors are each a different climate model simulation. The black line shows the one-to-one line, or a perfect prediction. And as you can see, after about 1960 or so, the neural network does a really good job of knowing what year it is from a single map of surface temperature. Now, you'll see prior to 1960 that the predictions are quite flat, and the network is always guessing around 1950. At first, my computer science colleague thought that there was something wrong maybe with his neural network architecture. But in fact, this has a science explanation. That is, prior to 1960, the signal is so weak and the noise is so large that the neural network is unable to predict the year. And it isn't until about the 1960s and beyond that an identifiable signal or reliable signal emerges, in which case the neural network is quite accurate at predicting the year. Now, the last thing you'll notice are the white dots. Now, what's really fun here is although we've used climate models to train the network to predict the year from a single map of surface temperature, it has never seen observations. However, we also have maps of surface temperature from observations. And so these white dots show what year the neural network thinks it is from observations, from maps of observed surface temperature. Now, if the neural network learned things from the climate models that were not applicable to the real world, these white dots should be all over the place. But instead, they largely fall along the one-to-one line, suggesting that the patterns and signatures the neural network has learned from the climate models are also applicable to the real world. Now, if you've been paying attention, you might think, hold on a second. Maybe this neural network is just looking at the global mean temperature. Why do you keep saying it's looking at regional patterns? So to make sure that it's not doing that, in which case it would be relatively boring, we also train the network after removing the global mean signal from every single map. That is, it can only rely on regional patterns since the global mean temperature of each of these maps is always 0. In this case, the network does not do as well as it did before because we've taken away the global mean information, that is, that temperature is going up. However, even so, the neural network still does a pretty good job predicting the year. And with observations, while it still is able to identify that the observations, that the year goes up, you'll see that the observations have now been shifted to later years compared to the climate models, suggesting that once the global mean is removed, the neural network thinks that the observed patterns are due to, must be in later decades, showing potentially an accelerated warming in the observations compared to our climate models. All right, so far I've made the point that I can predict the year of a map, but this is not terribly exciting, and everybody knows the year is 2020. Why would I ever train a neural network to predict the year being 2020? Well, this is where visualization tools such as layer-wise relevance propagation come in. That is, once we have trained the network to predict the year, we can now use LRP to go back and ask which regions are relevant for predicting a specific year. What patterns has the neural network identified? And in doing this, we can create maps like this. For example, this is the LRP heat map for predicting the year 2015 in these climate model simulations. And we see certain regions are really preferentially used by the network to determine the year. For example, the North Atlantic, as well as Eastern Asia and the Southern Ocean are all important relevant regions for the neural network's prediction of the year. Now, we can do this for more than 2015, and we've done this for many different decades. And you could stare at this for a while, but the first thing to note is that the neural network changes where it focuses. That is, the relevant indicators or regions for the indicators of climate change throughout the decades. We believe, for example, there are some interesting regions like over Southeast Asia that we think might be an indication of aerosol forcing and the network picking up on the impacts of aerosol forcing on temperatures over this region in the present decades. You'll also notice that the Arctic does not pop out as a terribly important or relevant region for the neural network's decisions. Now, if you recall, the Arctic had a very strong signal, a very strong warming with climate change. However, while the signal is large, the noise in the Arctic is also very large due to internal variability. And secondly, climate models disagree substantially over the timing of the Arctic response to anthropogenic forcing. Because of this, the neural network has learned to put its focus elsewhere in more reliable regions where the signal to noise is much larger. Now, often when I give a talk on this work, people ask me about uncertainty in these LRP maps. And I want to note that Dr. Zach Leib, one of my postdocs, has been developing a method to threshold these LRP maps, and that is to identify which regions are, if you will, significantly different from what one might expect from heat maps from noise. And in this way, we're able to point out which regions of these heat maps are really reliable indicators and which could be due to noise. Now, I want to end here with pointing out that LRP can also be used for the observations in this application. That is, once we put an observed map, for example, this top plot shows observed temperature anomalies from 1997, and we see the strong El Nino that occurred that year. We could now ask which regions were most relevant for that year's prediction. That is, where did the network look to determine the year from the observed maps? And we see that, for example, the Southern Ocean ends up being a very important region, although the anomalies there in 1997 were not that large. So again, pointing out that the largest anomalies are not necessarily the most reliable. And finally, we've been having fun with something called backward optimization. That is, if you remove the global mean and ask the network to predict the year, it gets it very wrong. I mentioned it's off by 30 years. That's shown in the top plot here. And with backward optimization, we can ask, how should we modify the observed 1985 map to get a perfect prediction? That is, if you will, what parts of the globe are making the neural network get it wrong? And by taking this approach, we are able to start finding where climate model biases may be most relevant for identifying forest change and observations. That is, that models are potentially too cold over land compared to the ocean, and that models are too warm over the North Atlantic within models compared again to observations. Now, I've gone through two examples of how we are using LRP for Earth science discovery, specifically in atmospheric science and climate science, but my group is doing others. For example, I already mentioned indicator patterns of forest change, but we're also looking at how extremes may change and what patterns the neural network identifies in those extremes. We're using it for longer term prediction like decadal predictability. Also, we're using it to think and learn about MJO dynamics, predictability, and teleconnections to the mid-latitudes. And finally, other colleagues here at CSU are using LRP to translate GOES, to understand how their network is translating, say, satellite GOES imagery to radar reflectivity and identifying the most important regions to the network for that conversion process. So to wrap up, my three big thoughts, hopefully I can leave you with today, are first that interpretable neural networks fit well within the toolbox of climate scientists. These artificial neural networks are not black boxes. Tools now exist to help visualize their decisions. And in my view, this is a game changer for our field. And as scientists, we need to continue to find opportunity to develop new tools that are applicable specifically to our fields. And finally, neural networks can be used for more than just prediction. We can incorporate science, or the science can be what the network learns. That is, we can get creative and have fun. Thank you very much.
Well, good afternoon, everybody. My name is Stephen Belcher. Can you hear me yet? Yes, you can. Good. Welcome to this question and answer session. So we had pre-recorded presentations earlier, but now you have, those of you online, the opportunity to speak live to our distinguished panel here and ask them some questions. So we've had some pop up as the talks were prepared. Perhaps I can just start by thanking all of our speakers. It was an incredibly diverse range of presentations and really whet the appetite for what we might mean by environmental intelligence. So I think one of the goals of our conference here is to think about what we mean by environmental intelligence and what diverse range of skills, etc., might be required to address that. What I picked up in the presentations was firstly the applications. So these are incredibly diverse, and Gideon, you gave us a DEFRA perspective, which is a great example of government policy and how science leads into advice. We might want to come back to that in the questions. Secondly, of course, climate and the pathway to a resilient net zero future came up in several of the presentations, and the use of AI along with conventional simulation tools and energy modeling, as Nick called out, is the second one. The third one, which of course is very close to the Met Office's heart, was around emergency response. So Wilco had his nice picture, well, not so nice picture, of course, of the flood in Italy and the diversity there. And both Nick and Gideon picked up on some of the emergency response. And then Elizabeth at the end picked up on the AI for understanding, which was one of Adrian Smith's themes for the Turing Institute. I think the second set of themes that I picked up was the data, the algorithms, and the visualization. So more of the technical stuff in the middle there. And Gideon, you talked about the data hub, and we've got some questions coming up on that DEFRA are putting together. There are issues around data quality, and I think we're going to go into that tomorrow particularly. Wilco, you talked about computer architectures and the need to align those to the data volumes. And this is something that's very live in the Met Office at the moment as we start thinking about our next supercomputer procurement and the 18 terabytes per day that are coming out of the Met Office at the moment. That will raise by an order of magnitude over the lifetime of our new supercomputer. We also heard about a very diverse range of applications of AI, from the post-processing of model output and data output to linking to the hazard to decision-making. Wilco, I think, made that point very clearly. And then the third and final strand that I drew out was the network and skills. Nick, you said very explicitly in your career how you've had to work with different other groups of scientists in order to deploy your AI skills to make services happen. And that's something I certainly recognize from a Met Office perspective. But something I'd like to come back to is something that Adrian Smith mentioned in his introduction around skills. And he used the term research engineers and data engineers as new professions that we might need to introduce. So I would put most of those things into the box of opportunities. And just to get this Q&A going, I wondered if we might talk about some of the barriers that our presenters see to the deployment of AI into environmental applications and the development of what we might call environmental intelligence, perhaps coming from the backgrounds that you do. So I don't know who'd like to start with that. Gideon, I can see you writing as the first presenter. Do you want to see, what do you see as the barriers from a DEFRA perspective?
Sure, I'm happy to kick off. Just, you can hear me, right? Yep, good. I touched on this in my talk, and I think, I'm much more of an empirical scientist, much more of a measurement-based scientist than many of the other speakers, I think, and certainly from a DEFRA point of view as well. Much of the data that we collect is ground collection, and I think the big blocker in terms of applying AI to that sort of data is that a lot of it isn't in the right format, isn't in an accessible format. We don't have the metadata attached to it, and we don't have it in a way that it's interoperable. So I think actually a lot of it's pretty basic. It's about data engineering and architecture to get stuff into the format that we can really start to use some of these fantastic new AI tools on. I mean, that's probably everything I need to say about my side of it. I'm sure others have got something interesting to add.
Brilliant. Thanks, Gideon. Who'd like to go, Nick? Would you like to go next? Yeah. Nick.
Yeah, so I completely agree with what Gideon's just said around sort of the data and the models, and actually what experience says at the moment is that actually many AI projects spend the bulk of their time dealing with the data, sort of getting the data into a sensible form, into something where you can actually then start using the AI methods on it. And there is an estimate that sort of data wrangling, getting the data in the right form, the right metadata, etc., is often as much as 80% of many projects, and that really does sort of show you the value of having well curated data sets, because if that can be done once and at scale and consistency, then actually everyone can build upon that. And as a country, we've been very much the forefront of what's been going on around open data, and the Open Data Institute is a fantastic addition to our landscape. So I think data and increasingly models. So I also spoke about digital twins. So that sort of, in addition to the data, the simulations that use that data are really important, because once you have those, you can start building upon them. I think another real challenge is around visualization of these complex data systems. I spoke about the global data observatory that we have at Imperial, and sort of that ability to understand this complexity and data and how a system is evolving and how it's changing over time is a real area of where significant research needs to be done. It can't just be the standard monitors that most of us spend too much of our days sat in front of. And then the final thing, I think, is the way that, building on that complexity, is the way that we as humans can interact with it and have the machines and the AI systems work well with us. So at the moment, many of us find interacting with computers a very frustrating endeavor because they're so unintuitive and so dumb from so many perspectives. What we want is a much better partnership model from the machine to be able to work with us rather than sort of us having to adapt all the time. And I think as you're in complex environments, you want that ability to work in partnership with the machines in a much more intuitive and easy to do manner. Thank you.
Brilliant, thanks, Nick. And I was very struck with your empowering humans examples, which play to that final point. Wilco, over to you. What are the barriers that you see?
Yeah, it's the barriers are the data wrangling and all the issues. Certainly, that's true. What Gideon brought up as well. That's clearly a big issue. If you look at the talks as well, you can see that all the subjects that come by are highly interdisciplinary in a sense, and brings together computer and data science and the domain science. Also in the last talk, and I think that's an additional challenge, that once we know how to make our data fair, interoperable, etc., that we also bring the methods and the domain science credibly together, and that's a part where actually the research engineers that you mentioned as part of the Turing Institute can play an important role. So that's where I really see a model that works. Secondly, it's the other part is the architecture, and it was just mentioned before as well. If the computers are complex beasts, and to handle them and to deal with them, especially if you go to the near real-time decision-making process around hazards, around digital twins, etc., we have to be able to overcome that burden to use that architecture. And there we probably can learn also from the ones that are more in the private sector. But that's certainly currently a barrier to make big advances.
Brilliant, thanks, Wilco. Liz, over to you.
Yeah, so given my background being a professor, I think a lot about education. And I don't just mean education of the graduate students, I mean education of the field. And so the last speaker just mentioned how we have to bring the domain science and these tools together. And personally, I think that's absolutely essential for a few reasons. One, these are complex tools, and at the moment, machine learning is still viewed very much as an art. It's not just a box you put everything in and then you wait a few days and something pops out that makes sense. It's really an iterative process. And if you want to learn something with it, no matter, even just make a prediction, you want to know that prediction should be trusted, that it's right. And thus humans are really an integral part of using whatever these tools spit out at the end. And because of that, we really need a workforce of domain scientists, of computer scientists who understand the domains and vice versa, that really understand what's happening and going into it and digging deep. Because ultimately, if we want to actually use the information that comes out, people need to trust it and sort of put their weight behind it. And I think we have a long way still to go with that. Especially, there's a lot of examples right now, say in weather forecasting, and just forecasters saying, I don't care what your numbers say, I don't trust whatever this machine is doing because I don't understand it. And so I think there's just going to be a lot at base level education that needs to happen before this is fully, as you said, a part of environmental intelligence.
Yeah, I completely agree with you, Liz. There are definite skills shortages, and from a Met Office perspective, recruiting these people is darn difficult because they're so highly competed over. Okay, I'm going to move now to some of the questions we've had during the course of your presentation. So These are largely directed at individuals, but I'll see if I can spread them around the panel members. So firstly, Gideon, Dave Topping asks, with many more networks and platforms and data-driven approaches emerging, what do you think are the biggest challenges to ensuring the evidence base to affect change is robust? So really a robustness question, and I'll perhaps come to Wilco after Gideon may want to comment on this one.
I'm sorry, Stephen, you broke up at the beginning of that. Can you just repeat the beginning of the sentence again?
I am terribly sorry. This is a question from Dave Topping. With many more networks and platforms and data-driven approaches emerging, what do you think are the biggest challenges to ensure the evidence base to affect change is robust?
Well, you kind of prompted me. I'm not quite sure how to answer that question. You prompted me in some of your earlier remarks by saying that there would be questions about quality control, and that's certainly a big point of any answer on this subject. In terms of the actual data that's feeding into things, making sure that the data is good is so critical. And you know, the old adage about rubbish in, rubbish out is very true. So that quality control and making sure that you're perhaps automating that quality control so that it's really smoothly done and not overlooked is important. An issue that we have a lot of the time, I'm sure this is true of all the speakers actually, is co-location of data, and that's another aspect which is important for robustness. You have to know exactly where the data is. You have to be sure you're on the same frame, and then you have to be able to extrapolate in a reliable way between data which might not be collected in exactly the same place, and that's certainly a big challenge. I mean, those are a couple of answers. Anyone who deals with data knows there's lots of things you need to worry about to make sure it's robust. I suppose the other overwhelming thing is that we have such an enormous demand on data that it's a case of choosing where we put our resource. There's so many things you could choose to measure. You have to be quite careful to identify what are the key things to choose, and that's an interesting interface between modelers and empirical and the observers. Sometimes I think that the observers can be challenged quite profitably by modelers saying, well, this is where we think we need the data to answer a particular question. So that's an interface that would be good to work on further in these sorts of groupings.
So I think I'd like to pass this question of robustness around the other speakers. Maybe go to Wilco next, and then Elizabeth, and then Nick. But to give them a moment to think, we at the Met Office obviously use data to initialize our forecasts, and we've started using AI algorithms more to spot busted data as we do that. So it's one of the elements of the kind of value chain that we're using AI. Wilco.
Yeah, there are various ways to looking at this. Indeed, to the data quality side and how valuable your data is in your data simulation system and what it does and the impact there. You could also see it more from a robustness point of view on how valid is the forecast or reliable that comes out. And that's more a standard approach, right, that you do in forecasting, that you always address reliability in terms of statistical metrics. That could be from a root mean square to Breyer skill scores, etc., that we've all been using. Up to more a physical robustness that I alluded to in my talk a little bit. Can a neural network learn the physics? So we see patterns, like Elizabeth has shown as well. You see patterns emerging that we understand mostly from our linear approaches to linear statistical approaches to data handling and data analytics. But we can also try to see, can it really learn more than these kind of linear relationships? Is it really the nonlinear dynamics of the systems that we know about, that we studied in detail with other kind of techniques? Can we say reliably? Well, that's a kind of robustness as well. It's other kind of knowledge that you test against your neural network or your machine learned system. So that's another approach to looking at robustness of these kind of methods and the data. And I think it can be done, actually, but it's a huge challenge, especially if it becomes turbulent. It's just then we have to look at it differently than we used to.
Good, thanks, Wilco. Elizabeth, your talk was largely around this question, so you have strong views on this, I think.
I do, yeah. I typically sound like a broken record on these panels because over and over all I say is, interpretability. I think it's what I'm excited about, and I think it holds so much promise. Because you were talking about the beginning, even just, you want to figure out what data is spurious. And at the simplest, maybe we would, it's very simplest when we had data just sitting in front of us with a piece of paper and a pencil, maybe we look for outliers defined by some threshold. And we would understand then why we were throwing those points out, because they exceeded, alpha or something. And so, in the same way, if we understand the process, not all of it, I mean, the whole, I think one of the reasons these tools are so exciting is because they're complicated. They can learn really complex nonlinear functions, and that's wonderful. So I mean, will we ever get to a day where we understand every single step and we can contemplate and picture it in our heads? Probably not, at least not me. But I think we can go a lot further than we are now. So I think we have domain scientists and computer scientists working together to develop methods for the environmental sciences key. For example, many of these interpretability methods were designed to identify, cats and dogs and dolphins and coffee cups in images. That's not exactly what we're doing every day. And so while we're using some of those tools, we're already finding that there's so much room to really develop these tools. And I think ultimately, if you want to talk about robustness, certainly there are other avenues as well, but interpretability and explainability in the decision-making process cannot be ever ignored. And if you ask another question, I'll probably bring it up again. As I said, I just feel like I say the same thing over and over, but I'm quite passionate about this, but also very excited about what the next few years are going to look like for us.
Thank you, Liz. Nick, what's your perspective on the big word robustness broadly applied?
Thank you. In agreement with all the previous answers to this, sort of having high quality data where its provenance and you're able to track that is really important in many applications. However, I think there are another whole class of applications where this is just unattainable. So I've done quite a lot of work in crowdsourced data, which I think is a really interesting area, and that sort of citizen science work in its broader environmental context is a really interesting thing. People out there taking measurements, taking observations with their mobile phones, and those data, or that data that comes in, will inevitably be not very high quality. It will have lots of errors. It will have mistakes in it, and sort of we and others have been working on some AI methods that actually try to make sense of that, knowing that your data is going to be uncertain, incomplete, and not at all robust or high quality. And there you're looking to use your AI techniques to smooth and to make predictions, to spot outliers, and to try and work with the humans associated with it. So not, where it makes sense, high quality data, good fidelity is really important. In other environmental applications, it will absolutely not be there, but we still have to be able to operate with it to take advantage of the citizens who might be doing that science, or some of the sensors out in the environment that might not just be very well calibrated or not very high quality results. And we have to, as this discipline, be able to cope with that.
Stephen, can I just back in on that really quickly?
Of course you may, go for it.
So there's something that Liz said that, and I think Nick touched on as well, which is important to draw out, I think, and that's if you use a system which is looking for outliers and chucks them out, you could be throwing out the very data that you're looking for. It could be the outlier that tells you the critical thing that the change that you wanted to see. So I totally support Liz's view that working with domain scientists who understand, okay, that's not an outlier, that's your signal, is really important. And I think that's inherent in Nick's answer as well, that you've got to have that sort of understanding of the data and work with the people who understand the data so that you know what really is an outlier and what's a signal.
Yes, one thinks of the ozone hole as an outlier. Liz, you want to come back briefly, please?
Yeah, this is a little off of robustness, but just sort of going off here. I think one thing that, to return to your first question, which was challenges, is that we already brought up interdisciplinary work, but this idea that to really make real progress, progress towards robustness, we really have to work together. And I know we talk a lot about working together, but normally it's like me as a climate scientist, working with a geologist or something. But when you're starting to take this whole other field that thinks about the world often quite differently than how I was trained, and to come together to develop these tools and learn each other's field a little bit, if you will, that is slow. And at least I'm excited and passionate, and I've been doing this for 3 or 4 years, and it sort of feels like molasses a lot of the time. But I think maybe one thing is although AI itself feels like it's speeding off ahead of us, there's going to be some slowness, I think, to really doing this correctly and right and making real solid progress. And being the impatient person I am, I have to keep reminding myself of that as we move forward.
Gosh, we have a tsunami of answers to this. Wilco and Nick, but brief, please, because we've got lots of other questions. But Wilco and then Nick.
Very briefly. Yes, well, I've worked also now for about 7 years on these kind of things, and it goes slow, but it goes fast at the same time. And well, we mentioned universities before. We started an applied data science master track in Utrecht, and the way that works is fantastic. The way the students pick it up very quickly. Actually the examples, the master projects that work on it, both from the computer science and from the domain point of view, whether it's health or governance or the geosciences. It actually works pretty well. So I'm pretty positive that we're advancing quickly. And sometimes I feel like an old person already. So that's good, I guess.
Nick, last word to you on this one, please.
I may feel like an even older person, but nevertheless, I've been an AI researcher for 30 years, which definitely puts me in the I've been around for far too long category. But one of the joys of being an AI scientist or a data scientist is actually the ability to work with lots of different domains, and sort of it's intrinsic. I have a tool, I have a set of methods that can be used for a whole variety of applications, way beyond what I would have envisaged when I started being an AI researcher and doing my PhD in it. So I think sort of as data scientists and AI researchers, we love working with domain people, because that's what it really does require. That we have tools, and tools need to be used for an application, and so I think you'll find very willing partners from our side of the table.
Thank you, Nick, and thanks to Dave Topping, which proved to be a very interesting question there. Slightly more specific one, and this is perhaps one for Gideon and for Nick, and it's around pathways to net zero. And Nicholas's particular question is, how will the infrastructure required for electrical vehicles be rolled out within 10 years? How can data science help with this? In your answers, you may want to broaden this to net zero more generally, but what do you think the role of data sciences could be here? And several of you spoke about the systems approach and the need to see this as a system of systems. I don't know who'd like to start on this one.
I'm happy to have a go. And I'm going to start by saying that I use that electrification of vehicles as an example in my government department about the level of challenge and the scale of ambition that we ought to have, because God, that's going to be hard. Going from a 7% market penetration to 100% market penetration with all that loss of tax revenue and all the infrastructure that's required in 9 years is just an incredible feat that DFT have set itself. And good luck to them, of course, because we all want to get to net zero. So rather than giving my thoughts about how they're going to realize that, I'll answer it from a DEFRA slant, which is how we're going to use data on our side is really, I think, going to be around how we optimize our land use, because the bits of the net zero problem that we have to face up to are very much about how we interact with our land, how we make our food, how we capture carbon on it, and how we combine our human use with the natural use of that environment. And that's going to take the data wrangling that we've talked about before, getting all the data streams that we have, and trying to optimize them. And it won't be just about physical science data and physical observations. It's very much across disciplines here. So we need to be dragging in data fields from economics, from behavioral science, from legal science, from who owns what kind of areas. And so it really becomes a data problem and a modeling problem if we're going to optimize how we can achieve what will be an enormous challenge in every sector.
Thanks, Gideon. Nick, I don't know if you would like to comment on the general issue of net zero and the role of data sciences.
Yeah, I'm going to specifically do it in terms of energy, as you per the original question. So I think sort of the smart grid, which is really what's required as we're going to move towards net zero, will be powered and driven by the sorts of AI and computational thinking that we've been speaking about during the course of today. So I think that's in terms of the way that the grid operates, very different grid, many different forms of sources of energy than there are today, and sort of the ability to handle that at a local, much more localized and regionalized level requires much more sophisticated software in terms of how the grid will operate in the future than we have at the moment. Actually, for much of the grid, we have exceedingly poor information about what it's doing, why, and what it's doing at what time, and if you make this decision, what will happen as a consequence. And then sort of more on the consumer side, you need advanced methods in order to deal with the scheduling and optimization of vehicle charging, in terms of routing of way that cars should go to make sure that the infrastructure is used and you don't just have some hotspots. And then actually in terms of planning what that infrastructure looks like, where do you put points, where do you put recharge points? Again, a classic sort of AI optimization problem. So I really see a whole range of those problems be using these sorts of methods and these sorts of techniques in order to address them. Thank you.
Great, thank you, panel, for addressing that question. We've got a whole basket of questions that are broadly around the relationship between AI as a data-driven science and simulation as a kind of physics-based approach. And I'm going to lead off with a question from Simon Vosper at the Met Office. So it was originally aimed at Nick. Could you comment further on the use of AI versus numerical simulations? There may be issues with training data, especially where the AI is being applied to predict in scenarios never seen before, such as climate change. And Wilco, you spoke about the use of AI to emulate the Lorentz 84 model, I think. And Peter Cox has got a question in the chat very recently asking if there are other areas of physics where the physics is being discovered through a data-driven approach. So I think these are all questions about sort of emulation of physics through AI. Wilco, do you want to pick that one up to start with, and then maybe move to Nick, and then if either of the others would like to comment?
Yeah, it's a good question, and it's the part where we feel a lot of reluctance from the field, of course, because we learned so much from the physics over the past centuries in a, like I said, reductionistic approach, basically. And now we're doing the other way around, starting from the data and trying to interpret what comes out of the data. And it's I still think that methodologically we learned so much from the physics and from how our world works that you can test these kind of things from an AI or a empirically learned model as well. And just as an example, whether such a system that I described, is it really chaotic or not from a nonlinear dynamical point of view? It's another way of looking at these deep learning methods. And I think we're not fully there yet. Mostly people look at these methods from an optimization point of view, and and there's a loss function somewhere, so it looks a lot like data simulation, and that you can mimic, of course. But that's different from really learning the physics or learning new physics or surprising physics, and that we. I guess I haven't seen that many examples yet. It's too bad that Liz had to leave currently, because the kind of examples that we see coming up is like, because our understanding is close to linear thinking, is that we find a relation between El Nino and something else, and because we knew that already from our almost linear thinking, we're glad we recognize that again from a system which fits very nonlinear functions, and that's, I think, we still have to develop there and still to see where we bring that together. So that's slowly emerging, and that really learning physical equations like we do right now. There's quite a few papers on trying to learn the Navier-Stokes equations right now, and really trying to learn turbulence. So I think we'll get there, but we're currently certainly not there yet. And then from Peter Cox, indeed, the interesting question is: will you learn new physics? Will something emerge out of the data which we didn't know before? And I really think that may happen. Because we may be too constrained on solving our current set of dynamical equations in numerical models, while the real world is much wider. And where I saw it happening already is not in the field of atmospheric science, but in the field of hydrology. In hydrology, the way they deal with numerical models is much more related to the estimation of parameters. And they don't solve basically a full chaotic system, but it's much more about the boundary condition and the parameters they estimate. And there they actually find new physics of that groundwater, soil, moisture system compared to what they traditionally do in the modeling. So I think there's scope there, but it's really low-hanging fruit has been done. This is the tough part.
Nick, I don't know if your experience of many applications you'd like to build on that.
Yeah, happy to. So I wouldn't draw such a distinction sort of between AI on one hand being something distinct over here and sort of numerical methods or other forms of computing being something entirely different. My view on AI is it's quite a broad church, and there's a whole range of methods that are used in it. Now, it's true that a lot of the interest in AI has come from data-driven and sort of learning models from data, but AI has always historically done model-based approaches to reasoning and inference as well. So incorporating model-based approaches is a well-worn tradition within AI. I think we will inevitably find new forms of physics when you start to look at these systems. If you look at what happened in the game Go as an example, when DeepMind developed a program to do it. This is a game that humans have played for thousands of years, and sort of there was an emerging pattern and consensus about how to play it. Moves you made, moves you didn't play. The AlphaGo system played Go differently to humans, and as it turns out, better to humans. And what's happened now is that humans play Go differently because of AI, and it's really broadened horizons and scopes. And AI will do that in many domains where there's significant complexity. Go is such an interesting game because it's so complex. And I would say that sort of human Go players have got to a local optima over the last 1,000 years. And actually, the AlphaGo program changed that optima, took them out of that local dip and put them in towards a more global optima, and that will happen with a range of different subjects, including atmospheric physics and other forms of models as well.
I think I'm going to move us on. I've got two more questions I'd like to ask you. So firstly, we've got, again, a range of questions come through from early career scientists, asking about, firstly, the skills they might need, and then secondly, some of the opportunities that might lie ahead in the intersection of these subjects. Gideon, you mentioned the civil service fast streamers. Could you give us some examples, maybe from a DEFRA perspective, of the kind of opportunities there might be for people with these kind of skills? And then maybe come to Nick and Wilco on the educational requirements of Wilco. I know you ran the Netherlands eScience Centre and may have some insights from that experience. So Gideon, start with you maybe from an applications perspective.
I think the opportunities are absolutely huge in this area at the moment. And Wilco mentioned earlier that the new master's courses are being very productive in his setting. I think that there'll be similar courses and similar skill sets will be productive everywhere because there is so much demand already for these sorts of skills, and it's only going to grow. So wherever you look, there will be opportunities. If you take Nick's answer about electrification and optimization of travel, then that's clearly an area where there's an enormous need for this. But everywhere you look, you'll see enormous need. Certainly, there's a big push across the civil service to hire more people with real data expertise and the ability to move smoothly between understanding real data sets and modeling them and using big data approaches on them. So that interface, I think there'll be lots of jobs in that area. lots of opportunities in the civil service, but similarly across multiple areas of industry and certainly in academia as well. And again, Nick's a lovely example of how he's got a hammer and he's been looking for nails, basically. He's been finding all sorts of interesting nails to hammer. And I think that when you've got a good tool, and this clearly is, this whole set of expertise is a wonderful tool, then you can find a lot of ways to apply it in almost every sector. That's a pretty generic answer, but I think that's the truth.
Thanks, Gideon. The man with the hammer.
Shall I say something about e-science and how we did that, Stephen? That may be a nice way to look at these things. And indeed, it's the hammer, but it's also the knowledge. So if you look at learning and how we look at it didactically, it's not only the methodologies and the competences around that, but combined with knowledge on systems. And what we did with the eScience Center, and proved to be very useful and successful, is to have computer and data scientists work at different domains and apply their competences for these different problems, but also let them go across these domains. So we let them work on one project in physics, but in the other, just 2 months later, work on a project in digital humanities. And it appeared that it actually worked, that you could bridge with these competences from one to the other domain, as long as you could also work as the domain specialist. And I think that's key. So it's key that you know about the competence, about the AI methodologies, about the data, about the software engineering around it. Of course, the way we talked about data, we hardly talked about software, but the main thing is software now, where we need to worry about as well. Or it's the next thing to worry about. And there the successful part is there really, if you couple the domain to the AI scientist, it works, but also if you cross domains, then you can learn across domains. And that really was very good on both sides, from the domain side and more from the machine learning or AI point of view. And in that model, it worked well. I saw I saw one of the presentations that e-engineers or e-research engineers are that idea is developing in the UK as well, and I would stimulate that a lot, because I saw a number of 25 for the Turing Institute. Well, put 2 extra zeros to it, I guess. That's probably what you need.
Okay, thank you, Wilco. Nick, over to you on the question of early career opportunities and skills requirements.
Yeah, and I would say I think the science program sort of around the world was a great forerunner for this kind of endeavor, really bringing computational and domain scientists together to work in close proximity, because that is genuinely what's required. I think sort of in terms of skills, and one of the great things about AI is actually the online courses that are available in this area and in machine learning are really high quality. So a lot of the original MOOCs and the founders of the MOOCs actually emerged from AI professors making their content available online, and out of those, things like Coursera grew. So actually there are some fantastic courses online for becoming upskilled in AI and understanding what it can do and what it can't do. So I would encourage folk to take a look at those. I think sort of the specialized masters courses or short form courses that build in expertise and sort of training or build upon domain expertise are really vital in these areas. So courses where you might take a computer scientist or a mathematician and sort of let him or her work with a particular domain, and also from the domain scientist, sort of the kinds of conversion courses that are available in terms of getting up to speed with AI and ML. So I think it's a rich ground on which to bring people together. But I think the good thing is that there's plenty of good courses out there, and for AI and ML, there's plenty of good toolkits out there that you can experiment with. It's not like it was 30 years ago, where actually you needed a PhD to build a neural network. Actually, now there are tools that are routinely available that are not too difficult to work with and sort of get your hands dirty and play with it and see what it's like and try and doing it for real.
Brilliant, thank you, panel. And just to support Nick's view about the Coursera, for example, as online training, I've had a look at that and it's really excellent. Okay, final question now, and I should have said earlier that unfortunately Elizabeth Barnes had to leave us midway through our panel, so thanks to her for joining us. Final question comes from Howard Covington, and I'm going to paraphrase. Howard is basically saying, given the climate change backdrop, what problem would you like to see AI solve? So this is your parting inspirational shot. Who would like to start with a problem that you'd like to see solved to help us navigate through climate change? Wilco, how about you?
Well, I think, and I'm glad it came up more. I think the problem to be solved is well, we know climate will change, and I think that even though you can never say science is settled, the science is actually pretty settled already, and the zero emissions was mentioned before. To me, it goes one step further on how then we can build. How can we act upon this in a good way? So how can we really bring the different disciplines, domains, sectors, etc. together to act upon it in a good, credible fashion? And that's where these digital twins thinking comes in, where you really work on scenarios which are not CO2 scenarios anymore, or emission scenarios, or land use scenarios. These are integrated scenarios on perspectives on how you can act, and to do that in well, what I would say near real time, and it depends on your problem whether near real time is the next hour or near real time takes a year. So the whole system we're working on should have sufficient low latency on an architectural point of view to make that happen, to make it possible. Earlier in the beginning, you mentioned the trouble of the supercomputing systems and the data to bring it all together and to act on it in a near real time way. So I would really say that's a challenge we need to pick up together, and it's a huge challenge. And if we pick that in pieces for different sectors, I think we can do it.
Brilliant. Thanks, Wilco. Nick, and then we'll come back to the DEFRA problems with Gideon at the end. Nick, what problem would you like to see solved to challenge climate?
Great question, Howard. I think sort of being able to determine what the impact of interventions might be before we make them, so that actually we have evidence-based interventions and really know where we can focus our efforts and what sorts of intervention would really make a difference, which is in essence is building upon what Wilco has just said. It would be great to know, to actually have the evidence to underpin that if this happened or if this happened, then these are the circumstances that are likely to ensue from it. And sort of as well as those interventions, I think the ability to be able to respond very much at the other end in terms of real time monitoring, particularly for things like environmental disasters or catastrophes. So to really figure out, ideally to be able to be ahead of them, to make predictions, to be able to prepare for them, but then to be able to respond in a very agile way to them.
Brilliant. Thank you, Nick. Now to the man who's charged with solving at least some of these problems. Gideon, over to you.
Don't put it on my back, please. And I guess I'll start with the rather clever environmental intelligence strand that we were pushed into using as our theme for this session. I think that's the area that we're all challenged with now, is being clever about our management and the way we interact with the environment. I think we're a bit of a well, we could have said this ever since Rachel Carlson's Silent Spring, but we're at a tipping point in the way that humans understand our interaction with the environment, and we need to move from the point where we're just using it to the point where we're managing it and understanding it and stewarding it into the future in a highly sustainable way. And that's about not just understanding climate and being able to interact with the climate system, but understanding how climate and humans interact with other things like biodiversity and the cleanliness of our air and water. So I guess that I see the artificial intelligence, and as Nick has touched on, the critical advances that we have in our ability to measure the environment in many ways, as enabling us to achieve what could be a real revolution in the way that we steward and look after our planet and make it more sustainable in the future, not just through climate, but through the whole array of environmental parameters.
Brilliant. Thanks, Gideon. You started with a big problem and you made it bigger. So congratulations. Well, on that note, and that very inspirational note, let's thank virtually our 4 speakers for a really entertaining and inspiring and thought-provoking set of lectures and set of questions and answers. So virtual round of applause and thank you very much. And with that, I will hand back to Kirstin Dale and Gavin Shaddock, who will wrap up for today. Thanks once again to the speakers.
You're welcome.
Hello and welcome again from Kirstin and myself. What an amazing afternoon of presentations. I think a superb set of talks from Elizabeth, Wilco, Nick, Gideon, and a really excellent example of how remote working can actually facilitate a Q&A session and actually interaction between both the participants through the chat and your questions, through to Stephen, who did such a superb job of chairing. I want to thank all of our presenters and the participants still with us at the moment, and really say a big thank you to everybody involved in day 1, which leads us nicely onto the topic of day 2 and tomorrow. So we hope that you'll all be able to join us tomorrow morning. We're going to kick off at 9 o'clock in the morning. We'll do a very brief, I promise you, introduction to the day from Kirstin and myself, followed by a presentation from Professor Vanessa Lawrence, former Director General and Chief Executive of Ordnance Survey, and then a presentation from Dr. Peter Durbin from the European Centre for Medium Range Weather Forecasts. Then we'll have a break, after which we'll hear from Dr. Ben Merton, Head of Professional Development and Academic Programs at the Alan Turing Institute. And then we'll have, similar to this afternoon, a panel discussion with the speakers, Vanessa, Peter, and Ben. And we would encourage you, as you've done so fantastically today, to pose your questions into the chat window, and then we'll pose those to the panelists. And then after another break, we are very excited about our poster sessions, and I'll hand over to Kirstin in a second to give more details of those poster sessions. Again, an attempt with our panel sessions to try to recreate what we might get when we're interacting at a live event in this remote setting. But more of that from Kirstin in a minute. And then after the poster sessions, we'll all come back together for a final wrap up and close. And so over to Kirstin now for some more details of tomorrow's poster sessions.
Okay, so tomorrow's poster session will be in 3 parts. Each part will contain between 6 and 7 posters, and each poster has a separate Zoom or Teams call that you can access through the link that you were sent in the guidance notes ahead of the conference. Each session will be hosted by the speaker, and the attendees can move freely between any of the talks in a session. Okay, so ahead of then, if you would like a sneaky preview of the talk of the posters tonight, the guidance that you were sent out has links in it, and if you click on the links, you can have a look at the posters this evening, and then you'll be well prepped for the questions tomorrow. So finally, I'd like to reiterate thanks from Gavin to our speakers, and to thank you all for attending and for staying, for coming back after all the coffee breaks. So thank you for that. I'd like to wish you a good evening and to say that I look forward to welcoming you back tomorrow at, I think it's 9 o'clock?
9 o'clock.
9 o'clock. See you tomorrow at 9.
Breezy.
Bye.
Bye-bye. See you tomorrow.